We are very happy to have everyone coming over here, and we have a wonderful program. We'll start with the tutorials, and we have the instrumentation demo this afternoon, and tomorrow there will be parallel sessions on different topics. But before we start, let's welcome our Dean Omachanu to give a welcoming speech. Thank you.
Thank you so much. Good morning and welcome to all of you. I want to acknowledge first the fact that what you're about to participate in is the brainchild of Dr. Pratim Biswas, who blessed the university with this amazing center and concept. So we're delighted. I just want to recognize you and thank you again for making this something that we're all here to participate in. Yes. So welcome to the University of Miami and welcome to Miami, the city itself. I hope those of you who have come from out of town will have an opportunity to explore the city and explore this beautiful campus. We're very proud of this campus, and I think everywhere you visit on this campus, I'm certain that you'd be pleased. And so please, I urge you to take a moment to do that. It is such a pleasure to be amongst colleagues and partners from all over. The work you do is principally powerful and compelling. Whenever we are amongst colleagues and scholars of this nature, I think it's important to recognize some of what you have done and some of what you bring to bear, even in a gathering such as this one. It is rare to find a more interdisciplinary area of scientific inquiry than the people who do work in the areas that you work in. Whether it's fighting the tyranny of the spread of disease or the consternation of having to work with environmental breakdowns and breakthroughs, you are constantly and principally at the center of research in this lane. I think the world recognizes the impact that you bring to bear. The work that you do remains compelling. I hope that in the next couple of days when you're here, I hope that you will take the time to strengthen the bonds that you have formed or you will form with other researchers. That becomes super critical. I also hope that you will deepen the relationships that you have already cultivated, some of you over the years and some just in the last couple of years. I think it is in that process that we rediscover the essence of scientific inquiry. So let those bonds be strengthened, let the engagements be more fierce and intentional, and hopefully in so doing, we can all prosper from the quality of your work. So thank you so much. I know you have a very busy day ahead. I am delighted to welcome you. Thank you.
Thank you very much, Dean Omachanu. So without further ado, we are going to start today's tutorial. But very quickly for housekeeping, the restroom is just behind us if you needed to use that. And also for people who are from outside of the university, you can have the free the Wi-Fi. You just search for CANE Guest. CANE, that stands for Hurricane. And that's so that's the free Wi-Fi you can use. Okay, so let's welcome the first tutorial speaker, Dr. Pratim Biswas.
Thank you, CY. While he brings it up, Vincent, of course, used kind words. Thanks, Vincent. But it's really a team effort There are 9 of us hardcore who belong to caste, as we call it, and each one is equally responsible for this wonderful effort. Several students are here. You saw the list of sponsors. Thank you. And NSF, we should also acknowledge NSF, which allowed us to bring several students here from all over. So do enjoy, as Dr. Umachanu said. And I don't know how many of you follow sports. A flying football is also an aerosol. Any particle that floats in air, it's a large particle. Sometimes we don't care about those things, but here on this campus, we do care. And I must say, go Canes. There might be all kinds of activities going on related to that. The game is on Monday. It is in Miami. If you stay over, do enjoy that too. Okay, back to your tutorial. I'm going to talk about portable sensors. People use the term low cost. I don't like that term, though it is indeed low cost compared to some of the instruments. We have several instrument manufacturers, and some of them, of course, make these devices too. So they are in that domain, but some of them are in, I would say, a high cost domain. We need all kinds of instruments. And I'll give you, of course, a description of portable and wearable sensors. How do I change this, Young? Just hit enter? Yes. It's stuck, I think. Let's see. I can't use these.
And then you can use the space.
Okay. Or this arrow, right?
Yes.
Okay, great. Thanks. Always technology challenged. So this is the outline. I'll talk about this. Of course, I have 45 minutes. I'll try to zoom by. If you're running out of time, some of the case studies, I'll go at a very fast pace. But this is in a tutorial mode. So I want you to pick up at least some of the important points, and do note some of the references for details. And if there's some time, I can, of course, ask some questions. So we'll start with aerosol instruments. You saw many of the sponsors. In fact, I think all of them make instruments. They are based on physical phenomena, and a particle that moves experiences a drag force. Just that simple phenomena of drag allows us to design devices known as impactors. And even the federal regulations, or the FRM, Federal Reference Methods, initially were based on that simple principles, which allow us to, this is acting up. Yeah. It shouldn't.
Normally.
They are based on, thank you. We'll have to keep calling you Young, the expert. So on the drag force, right? And that allows us to get those cutoffs of PM10, PM2.5, and you'll hear a lot of it as we go along. Then there are light scattering techniques, and many instruments allow us to be based on that scattering light. And then, of course, electrical mobility. Our interest is in classifying small particles, and I have to hit OK. Small particles. So we place a known charge on the particle, classify it in an electrical field, and then we can look at these things, right? And then, of course, it's very difficult to detect small particles, especially by light scattering. So we condense vapor, grow them, and then count them. So those are different instruments. We want to measure these in a very quantitative manner. And I know there are some instrument manufacturers here who also go into the colloidal domain, which means particles suspended in a liquid. But the aerosol community, we are extremely quantitative. We can count down to a single particle of different sizes and then go through the entire range and get a quantitative size distribution. You should be very familiar with size distribution. It is the number concentration as a function of size, right? Now, in some of the colloidal devices, you get a mean size, you get a size, but maybe you can't pull out the exact number concentration. Of course, there are advances in that domain too, but we take great pride in our community. This has been, of course, the basis from the very beginning. Many of these are research grade instruments. Now industry is adopting them, like clean rooms, synthesis reactors, and you'll hear some of these talks. Semiconductors are always in the news, and our community, of course, is driven by the environmental and atmospheric effects, but it is amazing to see the amount of industrial applications now, also of instrumentation. By the way, aerosol techniques are used to make large volumes of commodity particles. You know, the car that you drive, yesterday I had a flat tire, so I should mention they need to design these tires better. Carbon black is made by an aerosol technique. Titanium dioxide, fumed silica. If you had your cereal this morning, it was crisp because of some addition of you actually consumed nanoparticles. Okay, many of these instruments have a large footprint, of course, the cost which I mentioned, and sometimes not very amenable to measuring in adverse environments. I see I have a colleague from NASA here. We are getting ready to send folks to the moon, right? It's a very harsh adverse environment, and there's dust there, and we need to be able to, protect folks who are going there. So I'll just quickly walk through. There are instrument manufacturers here, so please take these prices with a grain of salt, but the size is of the order of magnitude. It's okay. About a meter, I told you about drag forces. This is a simple classification of particles, let's say smaller than 10 micrometers, 2.5 micrometers. It's a federal reference method. You collect on a filter, you control the flow extremely well because I want to get a concentration. It costs about that much. I can make them real time. This is the beta attenuation monitor, BAM as we call it for short. It's a real time sensor and so forth. I don't know if it'll come back. Of course, I can see it here. Okay, this is a little finicky, I think. The scanning mobility particle sizing system. This is an older picture. They're getting a little more compact now. TSI is here or will be here. And look at the cost is going up. Here, it's a mobility technique, and we get in real time the size distribution down to the nanometer particle sizes, right? And then people have wanted to miniaturize this. This also is a TSI device, a dust track sampler. I'm not endorsing any of the manufacturers, just these are just pictures to give you an idea of both the cost and the size. And then, of course, humongous systems. I also want to know the chemical composition. So this is a time of flight aerosol mass spectrometer. I presume folks from Aerodyne may be here. They are a collaborator with us. So these systems are large and they cost a lot of money. But in addition to the physical distribution, you can also get an idea of the chemical composition as a function of size. Okay, so can I make these things smaller? There's a definite need. I really like to wear one. I see Young has a nice face mask on. If it's a crowded area, you want to protect yourself, you want to know what you're being exposed to, or if you want a detailed understanding, the concept of wearable sensors come in addition to some of these other environments that I briefly mentioned. So optical sensors, there are two different types. I could do an ensemble measurement, which means I measure for the entire suspension of particles, or I could do single particle measurements, right? The accuracy, of course, depends on many factors. And it's been amazing. There have been innovations in optical engineering and things like solid state lasers. Before, when I started, we would fill up a big room with lasers and so forth. Now they have been miniaturized, photomultiplier tubes, photodiodes, and so forth, right? So these devices could be extremely low cost. And of course, in the United States, every room you will see there is a smoke detector that is basically detecting particles from a fire and setting off an alarm. Those devices now I can buy for, I mean, just the interior parts for as low as $5, right? And then can I put these things together? And then I think that's an AlphaSense block. That's a little more expensive, but it has a laser, it has a detector, and then of course also they could be all put together in a device, and I can buy these as low as maybe $100 all the way to a few $1,000s and so forth. There are all kinds of these things. So number of people are packaging them. I just came from a trip, but you must have heard of Purple Air, some of the data. Some of my former students themselves run a company now. I can't call it a startup any longer, APT, Applied Particle Technology, and they are working in the occupational settings. There are other things like Quantac. I think David Hagen is here. So please interact with people. They're actual manufacturers and so forth. I think TSI has a device too. This might be the wrong one, but you could, of course, learn more by talking to representatives from these companies. So it's proliferating, right? I just give from our own group, we've been using these things. So we went to India in the remote areas and measured emissions from cook stoves because they, burn biomass and it generates a lot of smoke. In Delhi, we were one of the first to distribute or place 28 sensors along with very detailed characterization, and did several studies. Now it's prolific in India, and India still, of course, faces major challenges. I list a few other cities. And we are now working with agencies such as NASA. Can we use it to detect lunar dust? Some of our colleagues in other organizations, including NASA, have sent some of these up to the space station. Firefighting, orchestras. We are, of course, coming off a pandemic, COVID. So some of these could be really helpful. Occupational settings, I mentioned Applied Particle Technologies, and they're doing fabulous in terms of helping out with the industrial hygiene aspects of occupational settings. So let's move on now. So go into this tutorial mode about light scattering. These portable and wearable sensors are based on optical techniques. So I'll just talk very briefly about light scattering. As I told you, it could be an ensemble measurement. So clearly we need a light source and we need a detector like a photodiode system or a PMT system. On the left is an ensemble measurement. On the right, if I somehow adjust the flow properly or design it properly is a better term, I can scatter light of a single particle and detect the signal and literally have a counting system and get the size distribution. This is really acting up, or maybe the equation was coming up. So the scattering intensity is based on the size distribution. And of course, it's also based on a scattering coefficient. It looks like a little complex equation, but it's nothing but integrating over the entire size distribution, because the scattering properties depend on particle size, depend on the refractive index, depend on the angle, the optical geometry, and so forth, right? So it is the intensity that we actually measure, or the scattering intensity. I am interested from some of these systems. You can pull out the PM values, right? PM, for example, PM 2.5 implies the mass concentration of particles below 2.5 micrometers, right? So from that signal, can I invert it to get a mass concentration, correct? So ultimately, that's the goal. And if you noted the last equation, I would like to get the PM concentration or the total mass concentration. So it's this one?
Yeah, this one.
And I'll use the arrows, right?
Yes.
Yeah. Okay. Hopefully it's more stable. So the total mass concentration is some kind of a calibration factor. You can already tell we need a calibration factor. And the intensity, the scattering intensity, because that will be measured. There's, of course, optical parameters, efficiency factors. I just call it eta. It's a sensor response coefficient and so forth, right? And this is, of course, an assumption. I'm saying that based on the scattering intensity and the calibration factor, I can pull out the mass concentration. So obviously, I need an appropriate fluid flow systems, as you saw in those two sketches. The quality of the optical device that I use. As I said, I can buy a very inexpensive one, and that's great. But then is it, accurate? The laser light beam geometric features. There are some very classic publications by this group, OIMET, and others who have said that even the width of the beam, the light beam with respect to the particle flow, you might miss the interaction. As you can clearly note, the particle has to interact with the laser beam or the light beam. And if you miss it, you're going to miss counting it and so forth. And then single particle counters have the problem of coincidence and how do we effectively integrate to calculate the PM levels and so forth. And of course, composition. All particles are not the same. I go to a firefighter system. The composition, it's a combustion aerosol. It's very different from what I might measure outside in the atmosphere of dust or other parameters. And then there's a dependence on humidity, temperature. All this tells me the calibration is critically important, right? So they need to be calibrated. That's the message we have to take. And you want to do this in a laboratory. Dr. Yang Wang here, now, of course, he did some fabulous initial work in looking at the calibration of some of these simple sensors. The other way is I could actually calibrate it in the field. There are these federal reference methods, instruments which are out there. Can I couple up? And I'll talk about, there are satellites out there which are also measuring things like aerosol optical depth. Can they be used in tandem? So that's a field kind of calibration. And the more the calibration we do, the better. I can cross-compare sensors. So the key factor is the PM mass concentration. I'm just reduced myself. I'll be very happy if I get an accurate PM level. Many of the regulations are based on that. And it's an important parameter. And can I pull this out from the sensor signal? Is the proportionality factor universal? We already know that that's a difficult thing that would happen. So it's no, it depends on the distribution and the composition, right? The refractive index. Of course, this is a sketch. Even if you go upstairs, you'll take a lab tour, you will see some of these chambers out there. So you want to use the more accurate instruments to give you the size distribution. And then you can plot, for example, the output of the sensor as a function of SMPS derived mass concentration. Or these are very precisely generated aerosols, and I can get their size distribution and mass concentration, and I can look at it. And you already see that for different types of aerosol, sodium chloride, sucrose, ammonium nitrate, the dependency is very different. If it is somewhat linear, that's great. I can have a dependence of the analog output from my sensor to an actual mass concentration. If it flattens out like the top curve, On the left graph, that's no good because it's only good till the linearity. And after that, though the mass concentration is increasing, the sensor is not detecting anything. And then I can compare to other more compact instruments which have been around and well calibrated with little more expensive optical components, the side pack, and so forth. So we can do things like this in a chamber, right? And then I take a picture. I just visited IIT Bombay. I saw Volker come in. I think he was there too. We had a great visit at the Asian Aerosol Conference. So there are fabulous facilities that you can set up and do these routinely. But you know that I need to generate an inlet aerosol, put it into a chamber, have some robust instruments to also measure them, and then place my sensors there, and I can do all of that. And on the top, I show at the roof of that same building, they have several BAM systems, and also they mount these, they call it the low-cost sensors, the portable sensors, and you can do a field calibration, right? So a lot of folks are doing this, and of course, they need to be done. I will point out some important factors. One is the importance of designing your calibration chamber. Hopefully it pops up there, is the flow distribution, because I'm going to place my sensors there and you might get a distribution in the chamber. So we did some very detailed CFD type calculations, and you want to find out exactly where to locate the sensor, where to do the sampling for the measurements. Otherwise, you're introducing inherent errors. So the PM concentration, you can see in that same chamber where depending on the location, I would have different concentrations. So I need to use this to appropriately place them. It's also important there's a mixing fan. So for the chamber, if you're designing one of these, you need to really have a certain pressure drop, a flow rate, a way of introducing the particles, and it's best to have some kind of simulation code. You can see the red dots are predictions of a CFD model, and some of these can then be used to guide the placement. Okay, so I'm just touching on important factors and so forth. Can I do a little better by understanding? This day, it's of course all artificial intelligence, LLMs. We hear a lot of that in training. I'm not going to get into that, but you really want to, and the AI models are more accurate with a physics-based integration, right? So here I want to bring in the physics in my calibration factor. Oftentimes it's a black box, and we need it sometimes. That the company gives us the calibration factor, but as researchers, we need to dig deeper, right? So with some additional knowledge of the aerosol, I can definitely do better. And again, recall that calibration equation. It's basically measuring an intensity and somehow converting it to a PM concentration. But I can put in the equations for light scattering, as I showed you before. And there are a lot of different notations here. The lowercase IDP is the scattering intensity as a function of size. And then I can derive an expression for the calibration factor, or that slope that a manufacturer might report. And I can play around with that equation, assuming that the particle has a certain shape of the distribution. These are all assumptions and not universally true, but many times the shape tends to be log normal, as we know in our field. I can put that in and try to integrate that expression out and come up with more compact expressions. But you see that the geometric standard deviation, the geometric mean size, and then of course the refractive index is thrown into those factors A and B. But if I have some knowledge, maybe I can do better. So using a calibration factor, so I need to have some knowledge of the aerosol I'm measuring. Many times in the lab, we do have it. I'm measuring it in an aerosol reactor, or if I'm doing it in the atmosphere, I get some idea. I can then reduce this error from 600% to 30%. And that is a tremendous improvement. And even though there are assumptions, we can really utilize this a little better, okay? I hope this is solved by the time the second tutorial speaker comes up, right? And third one. So please bear with me, sorry, but gives you a break to think about some of the things I'm saying and take your notes. And of course, the organizer will give me little additional time to finish the talk, right? So Virendra, I'm going to cut into your talk a little bit. So not respond. Yeah. I'll change this. Okay, so the market is flooded with these sensors. You will see that in the next slide when it comes up. A lot of folks are marketing these now, and that's great. We want that. We want some type of competition and different choices for the user to buy them. And yeah, I can go up a bit bigger. So we can cross-compare different sensors available in the market, and some are good, some are not so good. Some are good for my application, but not good for another application. So we can do that and come up with that. Yeah, make it bigger. Good. Thank you.
Yeah, I think it's somehow this one and that one.
Just
yeah. Do you want to switch?
Okay, so you can see the calibration on the screen. And yeah, that's fine. So for the different sensors, I can look at the calibration factors. I can compare them and then come up with, so, this works well. Of course, it's very dependent, as I said, on what system you're using and for what system and so forth. So, and these are not all the sensors available. This is a little dated in terms of the when we did this study, and there are a lot more available now. And but it is good to always cross compare and look at it, right? So some of them are ensemble instruments, some of them are single particle scatterers, and then you integrate it out, and you can see that on the right hand side is the ratio, right? So, and for the different types of particles, or on the dotted line is that ratio, and you see that you want it to be 1, correct, to the calibration aerosol, but sometimes it is over predicting, sometimes it's under predicting, and this is of course dependent on what aerosol I'm measuring. Incense is a combustion aerosol and so forth, right? So very specific, but just something that you could do and check out, and always good to do. So let's take the next step, because we have limited time here. One can dive in deeper into calibration. There are many manufacturers here, so please interact with them when you see your hands-on demonstrations and so forth. Can I do better in the design of a sensor? I now try to go futuristic. Lot of optical engineering innovations. I can get a red laser, a green laser, a blue laser. And they're very compact. If you go to the lab, you'll see these compact devices. And can I use all 3 different wavelengths now? I didn't bring up the concept of wavelength. It depends. The scattering intensity depends on the wavelength. Can I use all 3 colors of light? Measure the scattering intensities to get a lot more data. The detectors are getting to be very fabulous now too, and I can measure as a function of different wavelengths. I can also use a time of flight system, flow design to accelerate to different degrees based on size. This is again just a simple drag force concept. to separate it out as I get the scattering intensities, right? So these are, to my knowledge, not available. I can now begin to package this. So if you get to walk around the lab, you will see an optical table with 3 color lasers and a rotating table where the sensors rotate. We are just using one sensor and rotating it to change the angle of scattering and get a size distribution. So you can see you get different types of curves, and these might be helpful in better inverting the data and so forth. On the top sketch, you see on the right-hand side, we have coupled a electrostatic precipitator collection system, because oftentimes I also want to collect these particles for future analysis, right? Maybe the physical characterization or the chemical characterization as a whole may not be enough. I want to do some biological characterization. So we have miniaturized these ESPs and coupled it, and you can collect it directly onto your whatever these liquid systems and do a PCR type analysis and so forth. So all kinds of interesting things that the students can play with. And the key is to keep them small. That's the subject of my talk, so that maybe I can wear this and walk around and get significant samples. So for our firefighters, we are now beginning to planning to use these and put them on. This is more details on the data inversion you get in the Mie scattering regime. I mean, there are 2 regimes. I should have also mentioned that. It's the Mie regime that allows us to do a lot of different things with respect to the scattering signal and the inversion to pull out a refractive index. It's not that easy. It's not unique. There would be multiple solutions. So some knowledge of the aerosol again is important, or multiple wavelengths, multiple angles allow us to do this data inversion problem a lot more accurately. And we are showing you all the possible solutions at the bottom of the graphs, again, when it pops up. And of course, you want to see where they merge, and you can pull out and sort of some information on the refractive index. Okay, and we have then used this for lunar dust simulants, incense smoke. Of course, these are all in the laboratory, and you can see these factors will vary, and there is some deviation and a ratio of matrix. So from the multi-wavelength, multi-angle measurement, on the y-axis is the inverted size as a function of the true size. And of course, there is some variation and not always perfect, because even the, for example, lunar dust simulant might have different compositions and so forth, right? So, but this is what you do. Let's move on in the remaining time. How much time do I have? Young, you keep me.
7 minutes.
Okay. Okay, I'll quickly give you some examples of case studies, and I'll just zoom by very quickly. So one is we can integrate. I told you there are already many things out there. So this is some study from Taiwan, the Taiwan Airshed. It's a small country, and we can do some quick measurements. Satellites are beaming down, so I can invert it to get the aerosol optical depth. From that, some correlation to pull out PM 2.5. EPA monitors, they also have EPA, where they are mandated to have these federal reference method type instruments, BAM. And then the more portable and compact instruments, which I talked about. So these are some data. We did it over 2018 and just gives you average ranges. We use, so this is generating large amounts of data. So here, machine learning techniques can be brought to bear. And this is before your AI revolution with LLMs. So it's nothing to do with LLMs. It is more to use statistical techniques, but training your machine to do it, to pull out data which is robust, which is accurate. And if it's faulty data, drop it and things like that, right? So this would be a sketch where it shows you. So there are 77 EPA sites. NASA is beaming down twice a day, gives us 3-kilometer resolution. And then because these are lower in cost, I can deploy about 4,000 of them. Of the 4,000 deployed in Taiwan in that period, 2,356 were working well. So using the techniques, you can see half of them we had to toss out for variety of reasons. And then there's a concentration of these on the, I don't know which side it is, I'll call it the West Coast, facing mainland China, where most of the population resides. There are more mountainous regions and less population on the right. So you have a certain distribution. There's a way to convert the AOD to PM2.5. That itself is an art form. So you need to do that. But the net is, let's just presume we've done that. And we've got PM2.5 from the satellite measurements. And then you can use kriging to come up with all kinds of information, like smooth out the plots. So this is the PM2.5 concentration. If I only use the EPA sensors, I get the first curve. If I use only airbox, I get a little different, but maybe similar. If I use remote sensing, and then I can combine all of these together, and you can see the resolution. EPA station, it's about 560 kilometers squared. All the way, putting everything together, I can bring it down to 15 kilometers squared. So in addition to, of course, I could do field calibration that we talked about, but using all three, I can improve the resolution. And sometimes that's needed, especially from a public health perspective. And this was very interesting. In that period, we had a distribution which looked from the left to right over just a few days. Many times you will see that, oh, the industry is in the southern part of Taiwan. Let's hammer down on them when I see something happening on October 5th. But it also tells you that you can track using back trajectory analysis. It's not the industry in the south that is impacting stuff in Taipei on the north, for example. It could be things coming in from mainland China. And there was a typhoon. Of course, I need knowledge of the meteorology and things like that. And that's what was happening. So there's no point in curtailing emissions from industry in the south, but more so acting in a way that, yeah, you do the appropriate thing. So these combinations and these measurements begin to allow us to do that. I'm very quickly going through this. And of course, you want to validate it with back trajectory analysis and so forth. I'll skip through these. Now, kriging is a technique that is used to create those heat maps, as we call them. There is a certain impact of the wind direction, and we use neighboring sensors to smoothen out and get the heat map. But we know that the wind direction has a key role to play. So I can integrate the wind direction information with this kriging technique and modify. So we developed a modified kriging technique, which then enhances the accuracy. And I've applied it to, again, regions where there are many of these sensors. This was done in China. And you can see there's a significant difference of ordinary kriging with wind-corrected kriging information. Again, going through these very quickly, right? I wanted to point out about firefighters and fires because that's a topic tomorrow. We all talk about impact of wildfires and any kind of fire to us in the community, but there are people in the leading edge who are called upon, who sometimes even volunteer, and it's amazing. These firefighters, 68% of them get cancer. The general population, that's all of us put together, it's only 22%. So this is something extremely serious. So firefighters are very keen on understanding what is causing this, can it be reduced, and so forth. It's, of course, inhalation and also skin deposition. Now, there are many operations. So we have been doing this project following the firefighters. These portable sensors allow us to do that. They actually go fight a fire. Then they come out from the hot environment and they strip their clothes because it's so hot, they want to get out of it, they're done. That's known as gear doffing. And then they actually sit in their cars and go around. So we wanted to figure out which one is the most important. Each fire is very different. And of course, you look at wildfires, you will say that a firefighter should wear appropriate respiratory protection. They do that for certain types of fires. But when it's a wildfire, it's so hot, they don't like to wear anything. And obviously, that's not the right thing to do, but also the characteristic of the fire is different. So by doing all these studies for a structural burn, we found out that when they strip their gear, they take off their masks. It's not during the firefighting that they're exposed at the highest level. It's when they take off their gear and sit in the vehicle, because they often toss these things into the cabin, that they get the highest exposure. So the strategy to reduce risk, guide the firefighting operation really is enabled. These pictures on the right, one is a wildfire, another is a vehicle catching fire. What kinds of vehicles catch fire? Huh? Electric vehicles. Tremendous. It's not like your regular car catching fire. It's much easier to put fossil fuel induced fire compared to an electric vehicle, electric battery fire. And this has happened extensively now in many cases. And we are now beginning to put these, Miami is a test bed where cars will start flying. You often see autonomous vehicles, but for us, the cars will be flying. These are electric propulsion systems, very exciting because I could avoid all the traffic jams. But on the other hand, we have to be extremely careful about safety. So a lithium-ion battery, which is typically used now, if it catches fire, it's extremely problematic. It happened in South Korea in an electric vehicle showroom. One Mercedes-Benz caught fire and the entire showroom, all the vehicles were destroyed, to the point that South Korea was considering banning or slowing down this EV transition. So we work with our firefighters. We intentionally set one on fire, and the challenges are tremendous. Again, jumping through these, the number of electric vehicles that actually catch fire are much lower because of the lower numbers today, but this is going to go up. But to a firefighter, this is a tremendous challenge. So you design a region, different regions, different distances from the electric vehicle. You can mount these sensors on the firefighters. You can do measurements and look at the concentration levels. It, of course, shoots up. They are wearing appropriate gear. So it's not that they are being exposed to this, but you look at the gear doffing, the scale is off here. So even during doffing, the concentrations are high. There is resuspension from the clothes. So this gives you very precise information. Sometimes it would be difficult with the larger, more accurate instruments to do. And then the flame is suppressed, the concentrations go out. So you get a nice time scan to guide the firefighter. Again, going through all of this very quickly. But the message, we are engineers, we are problem solvers. In addition to protecting the firefighter, can I design my battery to not spew out such high levels of toxic materials, right? So integrating this with battery design right up front, and this is beginning to happen now. We have experts on batteries even in our department. And then what are some of these? This is, of course, during a training exercise, a whole range of PAHs, which are extremely toxic. And sometimes these deposit on the skin and then are picked up by the body. And that's why you get cancers in different places, extremely toxic. These are all carcinogens. And you can see the higher-ring compounds are in higher concentration. Here, of course, we had to collect the particles, bring it to a lab because there's no real-time measurement of some of these. Once we come up with some of those, that would be great to integrate all of it and get that information in real time so that you protect the individual from the basic things. And I'm going to go through this. I had a high school student come to our lab, and these high school kids these days have too much knowledge and tech information. So he put one of these sensors on a robot and he programmed it to go around. And instead of sending humans to fight fires, maybe the robot, this was an actual experiment we did in the lab, the robot could map out the path of lowest particle concentration, and maybe the firefighter could follow that. So it's an integration or a combination of robot firefighting, humans, and so forth. And this was just an amazing little project that a high school student did for us. So just in summary of firefighting, you can do this with AI guidance. You want to design specialty masks. Why are the firefighters throwing their clothes off as soon as they are done? So that's another part of the studies that could be done. So I'll just end there. It's really, these things could cause a social revolution. All of us should be clipping it. How many have this iWatch on? Let me see hands. Only 2, 3. I think students cost a lot. So students don't have it yet. But this is measuring I get excited presenting, my heart rate went up probably, but you can track yours. I can do a EKG standing here. So it's literally, we can be measuring on this. I want to mount a particle sensor. I want to be getting concentrations. Using these large data systems, I want to integrate it. I can put it on drones. I could put it on. So this is citizen science coming to the forefront. And it's not unusual. Physicians can figure out exposure to health. You know, there are a lot of asthmatics. If you're in a region and are prone to get an asthma attack, you have to rush to the emergency. If the physician could track it, or you could track this information, you're going towards a high PM region, you could say just get out from there or do something, wear a mask. So we could reduce ER admissions, right? Personalized medicine, source apportionment. I mean, this is all out in the open, and you are younger folks here, students, you're going to experience some of this in your lifetime. And then, of course, hook up to the cloud and so forth. So with that, I'll pause. Thank you for your attention. I don't know if there's time for questions, but I'll be happy to answer.
Okay, maybe we'll have time for like 2 or 3 quick questions.
Okay.
My name is Mike. I'm from Clarkson University.
Great.
It was a great talk. I have just one question. Like,
Mhm.
do you think what is the best way to find out how frequently we need to calibrate an instrument? Like whether we are doing on field or in lab, because what we've been taught that whenever we move an instrument, we need
Yes.
to generally do it. But
Very good question. I didn't even get into that. If I'm sending it into a firefighting operation, I can't be wearing that same thing in a dirty environment. What happens to all the optical systems, right? So in essence, it should, I mean, the more frequent you can do it, the better. Integrating with some other monitors and cross-comparing, it really won't take too much effort. Like let's say, move it close to a EPA reference monitor. I'm just picking that. Like in Miami, we might have 12 of those locations. You could, when you go closer, of course, getting it into the lab. So I don't have a precise answer, but the more frequently you do, the better, especially after a campaign. And in fact, it's a good question. You need to track it, right? Just like we oftentimes have to maintain devices and so forth. My air conditioning system at home, I do it once in 6 months, or a filter, we monitor the pressure drop. So here we need to have some integration of, let's say, the total PM measured. And hey, this is time that you just do it routinely, and so forth. So that's sort of broad answer, but a good point. And I didn't even get into that, but very important. The humidity, the temperature effects are also important. There might be multiple calibration.
because drift, like every now and then.
Drift, optical system would drift too. Yeah, we didn't get into all of that, but extremely important. Yeah. And we want these to be more and more robust, right? Yeah.
Maybe one more question.
Yeah, okay, Siwan.
Quick question. So not everybody has smart watches, but almost everybody has smartphones. I was wondering if there's anything we can do with cell phone cameras or, some of the fancy phones even have like.
Good. Every time you take a picture, I took one when the
There you go.
event started, I get a PM reading, right? Very good point. So that maybe, of course, it sits in my pocket. My watch is integrated to this phone. So even for data analysis, very good point. Right now, like I mentioned, APT, the company, they send it to the cloud. They're sitting there, a lot of inversion algorithms, and then they beam it back. That could all be sitting here. So very good point, and that's a good suggestion. A lot of young, smart people here. Hopefully someone takes it up and designs one. So maybe better than the watch in some sense, or easier, because everyone has a phone, as you said. Good, thanks.
Okay, well,
Yeah.
let's thank the speaker again. And maybe we'll take a shorter break. Now it's on my phone is 9:41, so maybe we'll be back at 9.
So they might. First one. Hello.
I think turn off
Hello? We can hear it, but it's cutting off a little bit. Yeah. No, we cannot. We cannot
Yes.
hear it. Hello?
What about now?
Yes, much better. Yeah.
But in the room, there is a lot of echo. So
Okay.
we think we're going to proceed by muting the audio to the online attendees because we want to prioritize the people in person.
Yes.
Yeah,
Yes,
we'll move ahead and then we'll share the recording later on.
sure.
Okay.
Sounds good. I think it's a better idea. Yeah. Mhm.
This one, can you view this one? Then I think.
Stop the echo.
Yeah.
Leave it alone.
That
Let him
backup
use.
speaker, not the microphone. I think the speaker maybe.
The speaker, yeah. Heard this.
Can you mute the speaker of what was it?
Yes, I think it's one of Dr. Wu's laptop is not muted. You can try to mute one of it. Yeah. What? Sorry? I mean, I cannot hear you.
You can send that.
Yeah, we can all send it.
Yes. Okay, let's start this here. So what my intent is to just introduce. So first is what's the definition of microplastic and nanoplastic? Earlier used to be less than 5 classified as microplastic. Now we have modified it and macroplastic more than 10 meter, mesoplastic between 1 and 10 millimeter, and plastic 1 micrometer to 1 millimeter, less than 1 is nanoplastic. You can get the idea just from the bottom figure what this means. Okay, For example, DNA, you can see the DNA is around 1 nanometer, and you can also look SARS, COVID virus, at the size of that. So this is just to show, so you get the feeling what that size means. Because are microplastic from the chemical PFAS. Yes, please. Thank you, Dr. Sama. So, essentially, there are different thermal treatment. So, once we have PFAS and microplastic, nanoplastic, do you think is it more difficult to destroy and go through the thermal PFAS? Just burning everything right? From solid landfill, solid waste, we are putting gas. So I think to thermal is thermal. You can heat it up things, so it's not difficult. So that's the solution you want at the end. That's the question by policymakers and people. But that's possible. Nothing extraordinary or to make that happen. Just burning.
Well, actually, we just probably the fever incineration.
Yeah.
Actually, 40% of the plastic we use, single-use plastic, they will end up in landfills or. But when you burn plastics, you have particularly pHs, SOBC fluorines, and those are highly precipitated. So it's not, I mean, incineration. I mean, if we control the emissions, that's a different story, but it's the way.
Personally, I think not.
Municipal waste incineration facilities are operating, they don't control nanoplastic. Also, you have plastic particle emission after treatment, so you will end up having a new toxic cocktail of compounds introduced in the air. So we need more sensors.
Breaking bounds is not an option. So how about breaking bounds and collecting, using it? Collected material. Let's have more discussion lunchtime. And there's
One quick question this time, not too familiar with all these plastics. I have burnt them too. Being a combustion scientist, we design a good combustor go all the way to CO2. But anyway, so the exposure on the risk, which I think someone was asking, is it more from inhalation, air, or is it drinking water? Is it known?
no, it's not known.
Which concentration level is high? Huh? So drinking in the water.
It's not just the water, it's also
Yeah,
Getting exposed. Yeah, it's everywhere.
much more than the air.
here we don't have pure indication. Even this person came out study using power. I mean, we need to develop an analytical.
We are running behind the schedule. I'm sure there will be a lot of discussion afterwards, but I think the speaker.
Like inside.
2 or 5 minutes, we're on time.
So what I did is I muted the room. So now I'm still can hear. I can hear a little bit.
Yeah, better.
I think it's just the sun.
Okay.
Then the different effect.
Test. For example, the is there a way to segregate them?
So is there still echoing? Yeah, there's still some. But in the speakers. Or maybe it's from some other computer. Hello? Still here. Hear from some noise from the building. I think now may be good. You can try Zoom. Hello, are you here?
Yes, very clear right now.
What about now? On
Very,
Zoom. Yeah. Okay. So
very clear.
so yeah. And you can tell us over class. Yeah. Okay.
raining out. We're going to start. Okay, everyone, let's get back to your seat. Okay, so we talked about the micro nanostar. Now we are going to macro, to the atmosphere. So we are very happy to have Professor Xu Wang give us an overview of the aerosol representations and the air quality market. Let's welcome.
Thank you very much for the opportunity. So today I'm going to talk briefly about representation of aerosols in air quality and climate models. So before going too far, you probably have heard of this term. George Box famously said, "All models are summary." Many of the people got excited, got caught really by the first half of sentence. All your models are wrong. Why? The microphone? Okay. Can you hear me well? How about now? Okay. All right, so I'll get started. So George Box famously said, "All models are wrong, but some are useful." Some people got excited and caught by the first half of the sentence, since all models are wrong, why do you still have a job? Well, throughout this fantastic workshop, you're going to hear a lot of fantastic presentations about all sorts of measurement techniques. These days, we have a wide spectrum of remarkable observing capabilities, but you can measure pretty much everything you want. But why do we still need models? Well, there are a couple of things, in a couple of ways models may be useful. Firstly, the models can tell you what's going on when and where you don't have observations. For example, if I want to take my kid to the beach tomorrow, I may pull up a phone and check what the weather is like. If I can measure the stuff on the beach, that would be fantastic. However, the measurements of the future is not available at this time. On the other hand, what's even more important, in my opinion, is that model allows you to ask what-if questions. Like, what if we don't have the Montreal Protocol? What would the ozone hole look like today? And what if we don't do anything about, carbon or pollutions? What would our future look like? There's something very remarkable that I recently found out that, back in the 70s, the scientists working at Exxon, the big oil company, they very accurately predicted the rate of global warming that is caused by carbon dioxide emissions. Back in the 70s, the models they were using back then was not anywhere close to in terms of the capability and the forecastability that the models we're using today. However, the point of if you have a clearly defined question, if you design a model that can capture the essence, the models can be absolutely sufficiently informative. And what you do with this kind of forecasting or the results coming out of the models, that's not a science question. That's our problem. All right, so today we're going to go through some high-level stuff. Firstly, we're going to take a look at aerosol size distribution. Then we're going to move on to see a couple of key aerosol processes. Then I'm going to switch gear to look at the chemical compositions and what are the processes and leading to these different components, producing these different components, the aerosols. And lastly, if we have additional time, I'm going to talk about a few emerging issues. All right, firstly, when it comes to aerosols, size really matters a lot. And you've probably seen this diagram a lot, comparing the PM 2.5 and the PM 10 with human hair. When it comes to ambient aerosols, the sizes actually span several orders of magnitudes, ranging from all the way from nucleating particles that is not bigger than a couple of nanometers, all the way to coarse gigantic particles that are as big as tens of microns. Well, if you look at the very left-hand side of the spectrum, the teeny tiny nanomole particles, the few nanometers, if you look at this range, the border between particles and gases are actually pretty faint at that point. Here we're talking about molecular clusters that are a size of a couple of nanometers. And then because of aerosol sizes span such wide ranges, normally people will use log normal distribution to describe the size distribution. And if you look at ambient particles, the size distribution, people found out, okay, the log normal distribution actually can pretty reasonably well capture the distribution of ambient particles. That's why the log normal distribution has been widely used in the modeling or in the atmospheric science world. And log normal distribution is a variation of normal distribution. As a result, it's carrying a lot of similar properties as the regular normal distribution that we're very familiar with. So, but how to represent aerosols in models? There are generally speaking, two different approaches. The first approach, as indicated by the diagram on the right-hand side, basically because aerosols span lots of very wide ranges. So in a model, we can have a number of different aerosol bins, and in each bin, we can have different aerosol components. In this simple example, I have only dust. I'm showing only dust, organic sulfate, sea salt, which are some of the most fundamental aerosol types that are represented in most climate models. However, recently we have been known this for quite a while that the agreement aerosols composition is a lot more complicated than this. So the modern chemistry climate models include a lot more details. But you can see that this kind of approach, in my opinion, this kind of approach is generally referred to as a sectional approach. Basically, have a number of different bins. This kind of representations are pretty close to first principles, and they usually can better resolve the size distribution. And in my opinion, the mathematics behind it is pretty straightforward. However, this kind of approach is computationally very expensive. Imagine that in this simple example, I have only 4 components, and if I have, for example, 10 different bins, only 10 bins, then you're talking about 40 tracers to track. We're not even talking about the aerosol numbers or even other properties. So the number of tracers to track in the models can grow exponentially with this kind of approach. On the right-hand side, I just mentioned, fortunately, in ambient particles can be reasonably approximated by the log normal distribution. So another approach that is very widely used, actually kind of a preferred approach in climate modeling, is a so-called model representation. In this kind of representation, we can chop off the aerosols in different molds and use the log normal distribution to approximate their distribution. So this kind of approach is computationally very efficient. However, you have to make some assumptions, because sometimes what if the aerosols, they don't exactly look like these normal distributions, and the mathematics behind it, in my opinion, personal opinion, it's a little bit more complicated. All right, so where do aerosols come from? Generally speaking, there are 2 pathways. Some of aerosols are directly emitted from sources, for example, combustion processes, or for the bigger particles of sea salt or dust aerosol, they can be directly emitted from mechanical processes. And on the other hand, there are secondarily produced aerosol particles in the atmosphere, meaning that humans or other sources would emit lots of trace gases. They can undergo complicated chemical reactions, eventually producing secondary particles. And then there are a couple of processes that are particularly important when it comes to aerosols. I'm going to go through some of them in the later presentation. Basically, first one's nucleation. Basically means the gas molecules sticking together and producing teeny tiny aerosol particles. And then once we have the teeny tiny particles, other condensable materials can condense onto that, basically grow the particles to bigger size ranges. And also particles in the atmosphere, they're constantly flying around. They can collide into each other. So coagulation basically means 2 particles colliding into each other, forming one slightly bigger particle. All right, firstly, we're going to take a closer look at nucleation. So nucleation, like I mentioned before, it basically means a process from which small molecules sticking together, producing small clusters, and clusters can grow bigger and bigger. So when it comes to nucleation, supersaturation is necessary, but mostly is not sufficient, because when you're reaching supersaturation, that means thermodynamically from the bulk perspective, the system has a strong tendency to form a condensed phase. In this particular example, is producing particles. However, when you're producing teeny tiny particles, you have to overcome the surface tension, the surface energy associated with surface tension. Unfortunately, for small particles, the surface energy can be pretty huge. So if you combine these 2 terms together, the red line basically depicts what the free energy looks like. Essentially, you have to go through this, go over this barrier in order for your particle to grow bigger. So this peak where this curve is usually referred to as the size of a critical cluster. So once somehow your particle grows bigger than this critical cluster, it can grow bigger and bigger like a snowball going downhill. And yeah, so that's about nucleation. So there are a couple of, generally speaking, there are a couple of different nucleation types. There are, for example, homogeneous nucleation involving only one type of molecule. These kind of scenarios is probably doesn't happen a lot in the atmosphere. And also there are binary nucleation involving two types of molecules, and ternary homogeneous nucleation involving three types of molecules. So in the atmosphere, binary homogeneous nucleation involving sulfuric acid and water vapor, and also ternary nucleation involving sulfuric acid, ammonia, and water vapor have received a lot of attention over the past couple of decades. And essentially, most of the climate models, they should implement at least these two type of nucleation schemes. Nucleation is basically a very hot topic for a very long period of time because science-wise it's pretty complex. But early studies, like I mentioned, focus more on the on the nucleation under neutralized conditions. However, recent studies showing that the iron-mediated mechanisms driven by neglected cosmic rays or radon decay actually play a quite important role. It means that in the galactic cosmic ray is pretty interesting. It means that the charged high-energy particles coming from deep space, they're constantly striking the atmosphere. And in the upper part of the atmosphere and also over the poles, the concentrations of these kind of high energy particles can be, relatively speaking, relatively higher. So the air molecules can be ionized, producing the ions. So ions can greatly accelerate the production of new particles. And at the ground level, radon decay actually plays a quite important role. Actually, for example, if you have a basement, it might be a good idea to have the radon levels tested because radons can be emitted from the rocks or accumulated because it's pretty heavy, can accumulate it in deeper spaces like a basement or crawl space. And the plot on the bottom left-hand side corner shows basically from a recent study indicating that the different type of nucleation mechanism happened in different places. We can see that organics actually plays a quite important role, and also aldyne species. These are the newly proposed mechanisms, and the importance of organics and aldynes were previously overlooked. This is a very hot topic of the research, by the way. And here I'm showing two more examples. The example on the left-hand side shows the field observations collected in Antarctica. Here in the middle panel, you can see the size distribution, and you can see the clear, rapid new particle formation event depicted by this kind of banana type of pattern. In the middle, they also observed very interesting events where the increased droplet number concentration, basically they experienced a fog event, and based on the measurements, they proposed that, okay, the fog events were largely driven by the new particles produced from that location. And on the right-hand side, I'm showing two maps, basically showing the contribution of new particle formation to the CCN. I forgot to mention that the reason that we care about new particle formation is that globally, new particle formation account for a significant fraction of the cloud condensation nuclei, but depends a lot on season, on where you're looking at, and also depending on altitude. For example, if you look at the upper free troposphere, or maybe sometimes in lower stratosphere, the new particle formation driven by the emissions from Amazon rainforest can reach 70–80%. But at the surface of the remote oceans, maybe the new particle formation driven by DMS or biogenic emissions might play a quite important role. All right, now we're going to shift gear and look at a slightly bigger size range, which is in the accumulation range. The accumulation range typically ranges from maybe tens of nanometers to a couple of 100 nanometers, all the way to maybe 1 or 2 microns. So the aerosol particles in these accumulation ranges are mainly produced from condensation, which means that an increasing amount of gas vapors condensing onto pre-existing particles. And coagulations may also play a role, but generally speaking, coagulations play a more important role when you have a large number of particles. And nucleation is mostly accumulation range particle, like I mentioned before, that mostly produced from the condensation of low volatility vapors such as sulfuric acid, or the low volatility organic vapors produced from oxidation of volatile organic compounds. However, if you look at ambient observations, it's frequently seen that aerosol particles in this range are, they often show two distinct modes. One of them is indicated by the small green mode here. That is the condensation mode produced from the condensation of gas vapors. However, there is maybe another slightly bigger mode in the condensation range that is centering at around a couple of 100 nanometers and extend all the way into beyond 1 micron. So studies have shown that, okay, if you start with condensation mode particles and try to grow the particles into bigger ranges by condensing the materials, it would be prohibitively slow to grow the particles into this bigger mode. So the condensational growth cannot, in theory, explain the presence of this bigger mode that we observe in ambient aerosols. So studies have proposed that this bigger mode is actually produced through cloud processing. For example, when you have aerosol particles that can be activated when you reach supersaturation, it can produce droplets. Droplets basically a big drop of water. It can scavenge soluble gases in the atmosphere. And for example, studies have found that sulfur dioxide (SO2) is moderately soluble. It can dissolve into the cloud droplets and undergo complicated chemical reactions, oxidation processes, and producing sulfate. And typically speaking, in ambient environment, the lifetime of cloud droplets are on order of maybe half an hour or something like that. And maybe that means that most of the cloud droplets that you produce would evaporate in maybe half an hour. So once evaporation happens, the water is gone. So the non-volatile stuff is that, for example, sulfate produced from cloud processing would remain in the particle phase. So the residual or the particles coming through the cloud processing would be bigger than the particles that a cloud droplet started with. So the plot on the bottom, I'm showing an example demonstrating that the aerosol population before and after cloud processing. You can see that. In the droplet mode, aerosol numbers definitely, in aerosol volume and mass of different components definitely increased a lot. And since I mentioned the water, I wanted to talk a little bit more about water. So water is a great medium for chemical reactions in the atmosphere. So under ambient conditions, many aerosol particles exist in liquid or metastable liquid conditions. That means, for example, if you take a completely dry aerosol particle, expose that in ambient moisture, it's going to absorb some water and grow into a teeny tiny droplet. But if you expose the water into more moisture, basically under supersaturated condition, the aerosols may be activated and grow into cloud or fog droplets. So when it comes to aerosols, relative humidity plays a critical role here. So when the relative humidity is below 100%, aerosols may absorb water from the environment, leading to basically a slight phase change. For example, I'm showing one example using ammonium sulfate particles as an example here. If you take ammonium sulfate particle, which is completely dry crystalline form, and expose that in certain relative humidity, if you gradually increase relative humidity, the particle will remain dry until it hits about 79%, and then it will rapidly absorb water and growing into a small, teeny tiny droplet. So this relative humidity level at which the solid particle was abruptly take up water, forming liquid droplets, it's usually called deliquescence RH or DRH. On the other hand, if you take a liquid ammonium sulfate particle and gradually decrease RH, once the RH falls below 79%, the droplet will not immediately lose water and become crystallized. And on the other hand, it will actually start to lose water and be crystallized at a much lower RH level. In the case of ammonium sulfate, it's going to be around 33% or something like that. So this RH level, this RH level at which the effluence occurs when reaching a RH level that's much lower than DRH is usually called effluence RH or ERH. So the ERH and DRH for different types of inorganic salts and inorganic aerosol salts have been archived in lots of studies. So you can use that kind of observation measurements to infer the phase state of the aerosol particles. So once the aerosol particles, if the aerosol particles are existing between DRH and ERH, so technically speaking, it can exist in liquid or solid form. However, in ambient particles, it's pretty safe to assume that most of the particles existing between those two RH levels have undergone several cycles of this kind of drying and humidifying processes. So in the ambient environment, it's relatively safe to assume the particles would exist in this kind of metastable liquid condition. So the volume of the liquid particles or liquid aerosols or liquid water content is where the aqueous phase chemistry can occur. So here I would like to draw basically do a quick comparison between cloud fog droplets and aqueous aerosols. This table summarizes some of the key differences. One of the major differences that you can see the first line from the first row that the liquid water content in cloud droplets and aqueous aerosols can vary by several orders of magnitude. This means a lot when it comes to chemistry and aerosol and cloud properties. One key one is that the concentrations of chemicals in the cloud droplets are much lower. So this kind of under kind of so-called dilute conditions. If you have much lower liquid content for aerosol water, on the other hand, the stuff dissolved in that teeny tiny amount of water would exist in much higher concentration. So the higher concentration basically would mean sometimes very different chemical mechanisms. For example, under dilute conditions, some of the reactions might not be entirely favored kinetically. For example, if you wanted to calculate the chance that a radical hits another radical under dilute conditions, the chance is pretty slim. On the other hand, if everything is concentrated, then the chance of radical reactions may become kinetically more favored. Another important factor is ionic strength. At a higher concentration, sometimes the presence of high levels of ions would play a negative or positive impact on the chemical reactions. All right, so we briefly talked about aerosol hygroscopicity. So that can be calculated basically, there are a couple of ways, but one of the pretty simple approach to calculate that is to use the Kappa-Killer theory. So this basically describes the tendency of aerosols to absorb water when exposed in moist air. So this kind of basically can be described by this one single variable kappa here. So kappa depends strongly on aerosol composition. For example, here on the table, I'm archiving a couple of typical kappa values estimated for ambient particles. For sea salt aerosols, the kappa value is pretty high. That means sea salt particles, generally speaking, are highly hygroscopic. And dust aerosols, basically speaking, they have much lower kappa values. That means dust aerosols don't like to absorb water as much. And organic aerosols, generally speaking, have lower kappa values as well. But studies have shown that organic aerosols from different sources, for example, from smoke particles, they have the organics in smoke particles sometimes would have pretty very different optical and hygroscopic properties. So the plot on the bottom left-hand side, I'm basically showing a couple of demo calculations indicating what the growth factor would look like under different RH conditions for two types of clusters or two types of aerosols, one with very low kappa values, one is higher kappa values. A couple of important things I wanted to draw attention to here is firstly, for teeny tiny particles, even if they're highly hygroscopic, they don't grow as much under high RH. That's because of the Kelvin effect, which I'm gonna talk a little bit more later. And on the other hand, for very non-hygroscopic aerosols or like dust aerosols, if you're exposed out under very high RH, ambient observations suggest that they would grow a little bit as well at very high RH levels. For example, dust aerosols in marine boundary layer exposed to like 80 or 90% of RH, they may grow a little bit. And all right, here I'm going to skip this slide. Basically, this talks about the Kelvin effect and the effect of vapor. Basically, the Kelvin effect describes the vapor pressure over a curved surface that is higher than that over the flat surface. That's basically, you can imagine that under a curved surface, a molecule under a flat surface, a molecule sitting at the surface is dragged by all the surrounding molecules. But imagine that if you're a molecule sitting at the interface of a curved surface, it basically has less neighbors to drag them around, so the vapor pressure would be higher. The Kelvin effect can be calculated. For example, for particles on the with diameter of 1 micron, the Kelvin effect pretty much can be ignored. But for particles with 10 nanometers, the Kelvin effect can be pretty significant. And okay, so previously we talked about the cloud droplets and liquid aerosols being a great medium for aqueous chemical reactions. So here I'm basically showing the phase transfer and aqueous phase process as a whole. So when you come, for example, if you want to calculate sulfate production from sulfur dioxide in cloud droplets, you have to, because sulfur dioxide is moderately soluble, it exists in the gas phase. So the first step to do is to calculate how much SO2 is going to dissolve into the aqueous phase. And then that's where the chemical reactions can happen. So these two differential equations basically describe the evolution of dC over dt. That means gas over dt means, grab the mouse here. That's fine. The first equation basically describes the evolution of soluble species in the gas phase, and the second equation describes the counterparts in the aqueous phase. And then the first term on the right-hand side is describe the chemistry in the gas phase or in the aqueous phase, and the second term on the left-hand side basically describes the phase transfer. I wanted to draw attention now. There is a two term here. The one is KT, that's describing how fast the phase transfer can happen, and the second term is basically describe the equilibrium. So the equilibrium. So this is a very important, a key aspect. For example, in many of the models, they just assume this gas aqueous partitioning happens, it reaches equilibrium instantaneously. Well, sometimes it's a reasonable assumption. Later, I'm going to show you that is not always the case. Sometimes it can take quite a while to reach equilibrium. And if that's the case, then if you assume a constant instantaneous equilibrium, you're going to face some biases here. And the KT, we can see that is basically consists of two components. Firstly, is the gas diffusion. That means the molecules flying around in the gas phase. And the second part is the surface uptake. It means that essentially describe the probability of a gas molecule striking its aerosol surface that actually stick to the surface. Because for most of the molecules, most of the aerosols, most of the gas molecules striking the surface would be, bounced back. And here I'm basically demonstrating that the SO2 and the hydrogen peroxide of the phase transfer here, these two things can actually undergo chemical reactions in the aqueous phase depending a lot on pH. But here I'm turning the chemistry off, just demonstrating the effect of the phase transfer process. Under pH of 7, you can see that it takes about 1,000 seconds for the SO2 equilibrium to partitioning to reach equilibrium, but hydrogen peroxide reaches equilibrium at relatively faster at around maybe 200 seconds or something like that. On the other hand, if you're looking at a slightly lower pH of 5, hydrogen peroxide would actually reach equilibrium faster at maybe still at 200 seconds or something like that. But SO2 here in this case would reach equilibrium instantaneously. On the left-hand side, I'm showing the basically solubility as a function of pH. You can see that at the pH of 7 and pH 5, the solubility would be quite basically the order flipped. So that means that for highly soluble species, it can actually take a while to reach equilibrium. And that's going to be a problem, for example, if you're running a model that has a longer time step. If you just assume everything reaches equilibrium instantaneously, then the results will be highly biased. I know the are here. I'm gonna skip this slide, but basically this slides describe the diffusion process in the aqueous phase sometimes can have a major impact on chemistry. So that is largely affected by the phase state of the aqueous phase. For example, imagine that a drop of water that's highly viscous. That is, the water has a low viscosity. But compared to, for example, a drop of honey that is highly viscous, and the chemical reactions happen this kind of under this kind of different phase states can be very different. So the equations are pretty dry and boring, but translate all that into human language. Basically, the mass transfer has a couple of steps. Firstly, it's a diffusion in the gas phase. It means the gas molecules flying around in the gas phase. And then secondly, if it wants to do anything with the aerosol or with a cloud droplet, it has to fly all the way to the droplets or to the aerosol and strike with the surface. And the surface collision is not all the collision would actually lead to uptake. For example, for sulfur dioxide, only about 10% strikes would actually lead to uptake. And the rest 90% or something like that would just bounce right off. But for other more reactive stuff, for example, OH radical, nearly 100% uptake would lead strike would lead to an uptake. And then once it's struck to the surface, there are a couple of things it can do. For example, sometimes it can undergo very rapid reactions at the surface, forming basically a difference between the surface and the bulk of the aerosol or droplet. And then it can also diffuse into the bulk of the liquid of the aerosol or the droplets. Basically means swimming around in the aqueous phase. And you can imagine that how fast it can swim in the bulk of the droplet would have an impact on chemistry. Essentially, you put all these things together, the slowest step here is going to be the bottleneck. The overall process is limited by the slowest step here. All right, so much for the chemistry. Now we're going to move on to see the last size range I'm going to talk about, basically the coarse mode. And the coarse mode basically ranges from a couple, maybe around one micron all the way to tens of microns. So these particles are mostly produced from mechanical processes. For example, the sea salt and sea spray aerosols and dust aerosols. These are heavily affected by, for example, near surface wind and stuff like that. All right, so when it comes to aerosols, one very important process, removal process in the atmosphere is dry deposition and also sedimentation. So these two are actually two different processes, but they're closely related. So sedimentation basically means gravitational settlements of the settling of the particles, because the particles may just fall down of the atmosphere because of gravity. And dry deposition is a slightly different process. It means that without precipitation, the particles come into contact with the surface and actually stick to the surface. The surface can be, for example, ground, water, vegetation, or a building, or anything like that. The point is, not all the particles striking the surface would actually stick to it, and dry deposition accounts for the process of sometimes being bounced away or that kind of stuff. So if you look at the formulation here, dry deposition actually depends a lot on gravitational settling, and then it's affected by other things. So dry deposition and the gravitational settling are usually described in terms of velocity. For example, the dry deposition velocity has the dimension of basic velocity. Here, the unit is centimeters per second. And it depends a lot on particle size, and also the surface type also play a quite important role. The rule of thumb is that for very big and very small particles, the dry deposition can be pretty fast. But for particles at around maybe one micron, something like that, the dry deposition can be fairly slow. That means that the aerosols, these kind of ranges can stay much longer in the atmosphere and undergo long-range transport. And here I'm gonna break down the terms, look at different processes. The figure on the left-hand side shows basically the dry deposition velocity and also the gravitational settling velocity for different size particles. We can see that for bigger particles, the dry deposition is largely dictated by gravitational settling. But for small particles, the gravitational settling can be ignored. But on the left-hand side, I'm basically break down the terms, the resistant terms, and we can see that for for small particles, Brownian motion actually plays a more important role, plays the dominant. But for bigger particles, interception may play a more important role. So all this together, we can calculate the dry deposition velocity and put that into the model. We can calculate that's a major sink of the aerosols in the models. All right, now we're going to switch gear and then take a look at the aerosol composition. And firstly, so this figure on the right-hand side summarizes the bulk aerosol composition measurements collected around the globe. We can see that most of the aerosols, the submicron aerosols consist of sulfate, organics, and nitrate, ammonia, all these kind of things. However, if you look at actual pictures of particles, one example that's shown on the left-hand side is that the aerosols may look like may have all sorts of weird shapes and also sorts of weird mixing states. For example, sometimes the sulfate may be internally mixed with organics, and sometimes sulfate mixed with soot. It can go very complicated. So pretty much, sulfate is a very important component in aerosols that is observed everywhere. So sulfate has, basically speaking, two different pathways. So firstly, we have a primary sulfate that's mostly from, for example, sea spray aerosols and also volcanic eruptions as well. And most of the sulfate in the atmosphere are actually produced from secondary reactions. For example, sulfate oxidation through the aqueous processing is one of the dominant processes of sulfate in the troposphere. In the stratosphere, SO2 oxidation by OH radicals plays a quite important role as well. So I briefly mentioned the importance of aqueous processing of SO2. That is a major sulfate source in the troposphere. So the idea is that basically sulfate is moderately soluble. It can dissolve into cloud droplets or aqueous aerosols, and where they can be oxidized by different things, for example, hydrogen peroxide or ozone or NO2, and also they can also be oxidized by oxygen, but that reaction is generally speaking quite slow. But if you have a teeny tiny amount of transition metals, the oxygen reaction catalyzed by transition metals can be pretty fast. So here I'm basically comparing the the relative importance of different oxidation pathways. The figure on the left-hand side, I'm showing basically relative importance of SO2 oxidation on wetted aerosols. So the different lines indicating different pathways, for example, it depends heavily on pH. For example, under highly acidic conditions, as well as lower pH values, the oxygen oxidation catalyzed by transition metals plays a very important role. But that line falls out rapidly at the higher pH because the solubility of transition metals can be limited at higher pH values. And all the other reaction pathways have a very strong pH dependence as well. But typically speaking, the ambient air, the troposphere aerosols, when you look at the pH, is maybe ranging between 1 and 4 or 5. So these are pretty relevant pathways. And I also have two sets of lines here, basically the solid lines and dashed line. The solid lines are calculated based on the kinetics we collected from dilute conditions. I mentioned before that under highly concentrated conditions, the ionic strength plays a quite important role. So the dashed line is basically correcting for the impact of ionic strength. So ionic strength in layman's term describes the actual availability of all those things that are available for chemical reaction. So mostly they can slow down the chemical reactions, but in certain cases, it can actually accelerate certain type of reactions. The plot on the right-hand side is pretty similar, but the same type of calculation performed for cloud droplets under more dilute conditions. We can see that the pH dependency looks fairly similar. The one interesting feature about the NO2 oxidation is that it spans a very wide range, and that's because the kinetics remains highly uncertain. Actually, in the cloud drop, in the aerosol phase, it's the same deal, but I took an average value here. And recent studies indicating that basically NO2 oxidation can be pretty important under fog conditions, because under fog conditions, that's when you can have fairly high pH and also fairly high level of NOx, especially if you're under urban conditions. All right, so one important thing I have to point out about the sulfur is that over the past decades, because of the global scale pollution control strategies, and the SO2 emissions around the globe has been decreasing significantly. But in East Asia, like India, in China, the sulfur emissions remains somewhat uncertain. But generally speaking, it's following a decreasing trend. So that means that the relative contribution or the relative importance of sulfate in aerosols have been decreasing. And if sulfur is not number one anymore, what is number one? Another very important component of aerosols basically nitrate. So nitrate is mostly produced from the chemical reactions involving NOx in the atmosphere. And during daytime and nighttime, the nitrate production mechanism can be different. So studies actually have shown that over the past decades, because of the successful pollution control strategies, sulfate has been gradually decreasing, making nitrate, and specifically ammonium nitrate, one of the most important components or contributors of submicron particles at least in the United States. And the figure on the left-hand side shows that shows the wintertime aerosol observations collected in northern Utah. We can see that at higher aerosol loading levels, ammonium sulfate actually is a dominant component of winter air pollution, the PM pollution in that region. And I'm gonna skip this side, but ammonia is basically the only basic gas that in the atmosphere that is at significant concentrations. Ammonia plays a very important role in regulating aerosol and cloud pH. And then organics. Okay, so organics are a very important category of aerosols in the atmosphere. And so organics can be fairly complicated. It may well consist of thousands, tens of thousands individual compounds. So organic aerosols can be directly emitted from primary sources. For example, sea spray aerosols actually contains quite high organic content, and biomass burning, globally speaking, is a very important source of organic aerosols, and also anthropogenic sources as well, like combustion processes. Or they can also be produced from the oxidation involving volatile organic compounds, especially VOCs emitted from vegetations and anthropogenic sources. So when it comes to the formation of secondary organic aerosols, the partitioning plays a very important role. That means basically that because of the complexity, there may be thousands or tens of thousands individual organic compounds. They all have very different volatilities. So based on their volatility, their tendency to partition into the particle phase can vary. So this equation, this kind of boring equation here, describes the partitioning of a particular molecule, organic molecule, the partitioning coefficient in the gas phase and in the particle phase. It depends a lot on the vapor pressure. So in order to calculate second organic aerosol formation, there are a couple of ways. Basically, firstly, mostly in the atmosphere, we start with the volatile stuff that are directly emitted. For example, isoprene emitted from vegetations or any other volatile organic compounds emitted from anthropogenic processes. So these VOCs can undergo chemical reactions in the atmosphere, producing a wide range of species. So we cannot track the partition of all the individual products. So instead, we can bin them into different products and calculate based on their volatility. For example, in the early days, there is a so-called two-product model that basically bins all the products into two categories. One is called CG1, the other CG2. Basically, one has higher volatility, the other has lower volatility. And we can calculate the partitioning for both of them. And later we realized the complexity actually in ambient particles is a lot more complicated than what can be described by using a two-product model. So people came up with this as a so-called volatility basis set or VBS approach. That is a lot more comprehensive framework, but conceptually I think it's pretty similar because instead of chopping them into two beans, we chop them into several different beans. But based on the volatility of the products, they can, roughly speaking, they can be categorized as low volatility VOCs or LVOC or semi-volatile or intermediate volatile organic compounds, and they all have very distinct vapor pressures. And here I'm just showing a very simple example of showing the second organic aerosol formation from toluene. So toluene is a VOC that is widely emitted from different type of anthropogenic sources. So the toluene oxidation can, in this polarization, a VBS scheme is producing SOAG 0, 1, 2, 3, 4, basically producing the products are binned into these 5 different VBS categories. They all have ranging from low to high volatilities. And then in the aerosol model, we mentioned before that we can have a number of different aerosol size bins. So in this particular example, I'm having 15 aerosol size bins ranging from 1 nanometer all the way to 10 microns. And for each bin and for each components, we calculate its partitioning based on their volatility and based on the aerosol sizes, considering the Kelvin effect and stuff like that. And basically, the first of all, from the figure on the left-hand side, you can see that the blue line indicates that, okay, once the oxidation starts, the precursor, or in this case, the toluene, gradually decrease. And the second plot, the big thick line shows the total second organic aerosol production started to increase dramatically. And the third figure on the basically shows the so-called this different kind of banana plot, but basically shows the aerosol size distribution evolution as a function of time. You can see that initially the aerosol size distribution peaks at around maybe 10 microns, something like that, and at the end of the simulation, the mold size increased to all the way to about 300 nanometers. And the plot on the on the right-hand side basically shows the partitioning fraction of the semi-volatile stuff existed in the particle phase. We can see that basically it depends on firstly volatility, and also the actual mass depends on the yield as well. So for example, SOA 0 here has moderate yield from the toluene oxidation basically, but that SOAG 0 has the lowest volatility. That's why SOAG 0 is one of the most abundant components produced from that. And SOA 3 on the other hand, is quite volatile. However, it has the highest yield among all these things. So that's why SOA 3 is one of the most abundant as well. So basically, that's the kinetic framework that people use to describe second organic aerosol formation in the modeling framework. And I'm going to skip this side, but basically in the real environment, organic aerosols can undergo complicated aging process, and that's can be a little bit more complicated. So I'm not gonna skip this detail from now. And then when it comes to organics, like I said before, if you look at from space, if you look at from the largest scale, the organic aerosols produced from biogenic sources plays a very important role. For example, isoprene and the terpene species emitted from vegetations, or from, for example, from Amazon rainforest or from the temperate forest in North America, in Russia, emits a huge amount of isoprene and terpene. These kind of things are highly reactive in the atmosphere. they can undergo complicated chemical reactions, producing low volatility species and contributing eventually to the secondary organic aerosols in the atmosphere. And on the other hand, we also have a bunch of organic aerosols produced from anthropogenic sources like combustion processes or this kind of things. People driving cars, that kind of stuff, emit lots of anthropogenic VOCs. And these anthropogenic VOCs can undergo complicated reactions as well, producing low volatility stuff, contributing to the so-called anthropogenic secondary organic aerosols. You can see from the simulation that the anthropogenic secondary organic aerosols are actually more abundant in the northern hemisphere compared to the southern hemisphere. And so we talked about some of the production mechanisms and also the different major components of different aerosols and also how they're represented in models. So this is one of my favorite animations showing the major aerosol components simulated by the NASA GEOS model. However, so for example, you can see the dust aerosols produced from northern Africa, and also carbonaceous aerosols basically coming from Amazon rainforest, and also sea spray and sea salt aerosols coming from the Southern Ocean. However, that's the model's way of representing aerosols. In reality, it's a lot more complicated. In the eyes of models, basically a sulfate particle is a naked sulfate ball that contains nothing else. A carbonaceous aerosol, on the other hand, is a naked organic ball that contains nothing else. In reality, it's a lot more complicated. For example, on the photo on the left-hand side, I'm showing the so-called aerosol mixing state, basically photos of actual aerosols collecting in the environment. We can see that we may well have a small fraction of soot particles attached to sea salt aerosols and to mineral dust aerosols. And then we can also have soot particles produced from combustion sources. They undergo chemical reactions, have a bunch of sulfate or organic stuff attached to them. So that means that in the ambient environment, actual particles would exist in very different mixing states. So the plot on the right-hand side demonstrates why mixing state is very important. That is why it's underrepresented in models. For example, in this example, we have the aerosols consist of 50% ammonium sulfate, which is highly hygroscopic. And the other 50% is, let's say, it's just consists of hydrophobic organic aerosols. That means on a higher RH, the hydrophobic organics won't grow much as well. And in a highly idealized condition on the left-hand side row, we have internally mixed. That means each aerosol particle contains 50% of ammonium sulfate and 50% organics. They are well mixed. So because 50% of aerosols consist of highly hygroscopic ammonium sulfate, if you expose that under higher RH, all 6 aerosol particles will be activated, producing cloud droplets. In the middle, we have the 100% externally mixed particles. They're just naked ammonium sulfate particles and naked organic particles. Well, obviously, the hydrophobic organic particles will not be activated under higher RH, but the ammonium sulfate particles will. In this case, only 3 particles out of 6 are activated. In the more realistic scenario, every particle may look slightly different. So we have to track the hygroscopic growth for each type of individual particles. So in this particular example, maybe 4 or 5 different particles out of 6 are activated. So the actual mixing state would heavily affect the aerosol, would heavily affect the mixing state and hence the hygroscopic properties. So in the model, currently, most of the models are not accounting for this kind of things. That's a very active area of research as well. So I'm not sure how much time do I have. Great, fantastic, perfect timing. Okay. In the end of the presentation, I'm going to wrap up with a couple of more emerging issues. We have been talking about PM2.5 a lot. So PM2.5, people care about that is because the size is small enough so they can undergo long-range transport. We mentioned before that the dry deposition of PM2.5 can be pretty low. And also PM2.5 can, once you inhale PM2.5, it can deeply penetrate all the way to the lungs, so have major health impact. So thanks to the Clean Air Act, over the past couple of decades, the PM pollution in the US have been improving in multiple places. With one example, if you look at the plot on the left-hand side, that in the Western United States, where's the wildfire-prone regions, the air quality actually has been worsening. That means the decades of air quality gains, thanks to the Clean Air Act, has been partially offset by the increased wildfire activities in the Western United States. States. On the this small on the right hand side shows exceptionally intense wildfire year basically in 2023. That is the elevated PM2.5 levels transported all the way from Canada. You know, the one thing about pollutants is that they don't respect political borders. So whatever coming from this study, we can blame that to the Canadian wildfires, but you know, there's very little we can do about this kind of stuff. So another important issue is the winter air quality. So very recently, the EPA has lowered the ambient air quality standard. I forgot details, but basically, I think the 24-hour average is decreased from 13 micrograms per cube or something like that all the way to 9 micrograms per cube. And because of that, many of the counties in the United States would become non-attainment to the new air quality standard. If we look at a couple of examples showing in different regions, the winter air quality start to stick out. And because there are a couple of practical reasons. For example, in winter times, the boundary layer would be much shallower, so whatever emission we emitted from the surface would be trapped there. And also all the completed chemical reactions, daytime, nighttime chemical reactions happening in the winter boundary layer would actually promote the formation of a different type of aerosols. The recent study indicating that the ammonium nitrate is actually a pretty important component, and also the organics from the combustion process and that kind of things are major contributors. And with that, I'd like to wrap up and I'll be taking any questions or comments. Thank you very much. Right. Right. I'm a computer nerd, not an expert in measuring pH, but I assume for precipitating waters, you can just collect the rain samples and dip your pH sensor into it and measure that. For aerosols, stories are a bit more complicated. There are methods. Recently, people propose different methods to actually measure the pH. But in the modeling world, we usually use the thermodynamic models to calculate the acidity or pH for aerosols. That would require basically the composition of the aerosols and also the gas composition, especially ammonia and the nitric acid, all these kind of things. So long story short, for aerosols, we computer nerds mostly calculate that using models. But for cloud pH models, there are ways to calculate, relatively speaking, simpler than aerosols. Yes. Great question. So, yeah. The question, if I understand correctly, the question is basically with all the aqueous phase or hydrogenous chemical reactions happening, the composition would change, the pH will also change. Then how would the change in pH and composition be reflecting the chemistry? Am I? Yeah, cool. So I personally like the sectional approach because mathematically it's easier, computationally it's more expensive. But if you use this kind of this sectional approach, basically in each size beam, we track all the different components. So at each model time step, we calculate all the change in composition and also the corresponding change in pH would also be reflected. So in a sectional approach, everything is tracked in the proper way. But in reality, we have to consider the time step. For example, essentially you're solving differential equations. And if you're taking very, very teeny time steps, it would take forever to finish the simulation. That's not ideal. But if you take a very long time steps, basically you're missing lots of the details, sometimes making your solver unstable as well. So find a sweet spot for the time step and solve everything within the time step and track everything.
needed initially.
Right.
Same with discrete section.
Yeah.
Those last question, everyone doing machine learning, is that your views?
Okay, the two questions. Firstly is can the models use some sort of adaptive time steps into basically, and second question is about application of machine learning. So the first question, the models do use that, and actually when it comes to chemistry and dynamic processes, the model have very different time steps because we cannot use very fine steps for very large scale processes because that's just computationally not a good idea. And when it comes to chemistry solvers, sometimes there are adaptive time step solvers, but that usually involves iteration. And that definitely is happening in the more comprehensive models. But in big models, I would say people have tested a lot. We understand the system reasonably well, so we just pick a time step that would basically balance everything. But the adaptive time step is a very widely used trick in our world. And second question about machine learning, it's definitely one very buzzy word. There are a lot of things. I myself am a big fan. I use machine learning a lot. But in my opinion, there are two type of things I use machine learning for. The first type of observation is application is that there's a process I need to resolve in the model. There is no good physics-based model out there, but there are lots of observations, sufficient amount of observations, so I can grab the observations, process that, train a machine learning model, pretending that we're doing proper things, so that we're learning stuff from observation. The downside is people have doing these kind of things a lot. They train the machine learning using satellite, using ground-based observation, blah, blah, blah. The downside is that the machine learning models can be tricky. For example, if your observations are highly comprehensive in terms of imagine that you have a number of high dimensional hyperspace. If you have a comprehensive training data set, then fantastic. If you only have observations cover very limited regimes, then the model is going to make up things in scenarios they have never seen. That problem is called overtrain. An overtrained model is, in nicer ways, it's useless. So yeah, have to be careful. Another type of application is that, okay, there is a physics-based model that can appropriately solve the problem, but that's too expensive to scale up. For example, the very high resolution, highly detailed physics-based model, in the foreseeable future, it's impossible to scale up in big models. What can we do? Okay, we can grab the physics-based model, run that for many times, and build a comprehensive training data set, train a machine learning model, and put that into big model, pretending that we're running a fancy model in the big coarse resolution model. That's a very popular approach that I'm currently doing. So there are other ways of using machine learning as well, but that's a very, very hot topic these days. Yeah. Yeah. So the question about modeling of nanoparticles and health impact. So our models, we do have nanoparticles, but the composition are heavily depending on what are the sources. For example, for nanoparticles, we have the black carbon from combustion processes and the sulfate and the organic coming from all these sources. But in reality, there might be other type of particles. So sorry, I need to mention that in the models, we also represent some of the trace metals or some of them for toxicity reasons. But anything we can resolve, that's fantastic. But because of the limitations of models, there are uncertainties associated with that, and there are bioparticles and that kind of stuff. And in most of the climate models, I would say that they're not fully represented yet. Some of the specifically designed models may have better capability in capturing those kind of things. But I would say for bioparticles and health impacts, most of the models are probably not designed. Most climate models are not, at least.
But before we go to the third floor for the demo, we're going to come here so they can give you a flash of get to understanding what about lunch. Okay, so remember to bring your badge. It says test, right? So that's your ticket to the cafe. And our cafe is just new and just will be a good walk, especially after when I start. Now it's beautiful outside, so you can see our beautiful campus on the way to the cafeteria. The cafeteria, of course, we have a map. Is that good? Or we have a few students who are also going to go there. So you and the student can raise your hand. You are going there. You can follow.
You can put it on top of this laptop. That's okay.
If I do audio on mine, will that, how do you want to do the audio? Is audio coming through here or through me?
Through you, should be through me.
No, audio going through
Audio
this.
through here? Oh,
Okay, so I'm muting myself and I'm talking through you.
Yeah.
Okay.
You can put
Sure.
it on the all.
No, it should be okay. No, I think it's better because otherwise you're making it more slanted. Hello?
Okay, welcome back, everyone. Hope you had a good time in your lunch conversation with us over here. So this next 30 minutes is about the flash talk from companies that are going to demonstrate their equipment instrument for aerosol and nanoparticle measurement based on physical, chemical, or biological properties, depending on the need of your application, right? And for us to do these aerosol or nanoparticle research, instrumentation is very important because without that, we cannot really measure what we want to have, right? We cannot capture what we want to have. So we are really, really happy to have these companies coming over here to demonstrate their state-of-the-art instrumentation. That will be of interest to us. So 7 of these will start from Melbourne. Okay, that's welcome.
Thank you.
Thank you so much. My name is Raghu Ragat. I'm a senior scientist with Malvern Panalytical. And just to recognize the brand, we are now Malvern Panalytical, Micromeritics, and SciAps, a powerful combination of a few different companies This is kind of a recent combination. So you see Malvern Panalytical on my slides and then micromeritics on another slide. Just know that we're all combined now for the next this talk and 2 more talks. So what you're going to see in the lab today, from my perspective, is the NanoSite Pro and the Zetasizer. These are 2 very complementary techniques to enable people to calculate the size and the concentration and zeta potential and fluorescence and all these different metrics. And so I'll show 2 slides. The first slide is really how these 2 technologies are similar in nature. One is that they're both, produced by Malvern Panalytical. They both will measure particle size with different ranges, so they're very complementary to each other in that respect. They both use light scattering as a fundamental basis behind the physics on how we make those measurements. They can look at temperature. They can look at viscosity of your sample. We are reporting the hydrodynamic size, so it does assume particles to be spherical. We can get into some nuanced conversations about how we can get maybe some dimensional analysis with a Zetasizer, but essentially we're looking at the hydrodynamic diameter, which, for anyone who, maybe not in the particle world, that is the spherical equivalent of a particle diffusing at the same speed as your sample. So, if you've got something that looks, elongated, the hydrodynamic diameter might essentially reflect, the longer dimension. You do need to know the temperature and the viscosity of your sample. Spherical, between the 2 technologies, it says 160,000. The number now is up to 200,000 or more publications that cite the 2 different technologies. So somewhere has done, published on research that's probably similar to yours. So, Google Scholar is a very powerful tool in this respect. They're both relatively small. They're both benchtop systems, probably about the size of bigger microwaves, if you think about it. And, the software is pretty easy and intuitive to use. You'll see that when we go upstairs a little bit later. And so, highly used by various people in academia and industry. So let's get into a little bit of the differences. So the NanoSite Pro uses a technique called nanoparticle tracking analysis. We're looking at the light scattered off those particles move around in Brownian motion and tracking their movement on a frame by frame basis with a camera. So then we use that to determine their size. So that's a slightly different version of the Stokes-Einstein equation. Dynamic light scattering is what the Zetasizer uses. And that is fundamentally looking at how, a fluctuating signal coming off particles might change over time as the particles continue to move in Brownian motion. So we correlate that change based on their initial time point. And I'll further describe this tomorrow when we give, a longer talk. The resolution for NTA is higher. It is a number-based distribution. So it enables people to actually gate and say, okay, what is the percentage or the concentration of my particles between 46 nanometers and 212 nanometers, right? So then you can get percentage and the concentration within, that size range. And so we say that the NanoSite Pro has a typical resolution of 1.2 to 1 in terms of peak-to-peak difference. The Zetasizer has a wider size range, but it is a bit lower in resolution. So the typical resolution is a 3 to 1 peak-to-peak ratio. We do have a couple iterations of our Zetasizer that can bring that down to a 2 to 1 peak-to-peak ratio, meaning you can distinguish a 200 from a 100 or a 10 from a 5 nanometer peak and so forth. As I just mentioned, the NanoSite does use a number-based distribution, which is why you can get the higher resolution with NanoSite. And the raw form of the data that comes from the Zetasizer is an intensity-based distribution. So we're looking at how light scatter off these particles. If your particle is larger, then the light intensity will be proportional to the 6th power of the diameter. So if you're looking at a pretty polydispersed sample with considerably larger particles, your data might be a bit weighted towards the average diameter reported might be a bit weighted towards larger particles. So numerically, the size range for analysis with a NanoSite and nanoparticle tracking analysis is about 10 nanometers to 1,000 nanometers. If you're looking at metals and metal oxides, that lower limit is around 10 nanometers. If you're looking at biological samples or polymer-based samples, synthetic-based samples, that lower limit might be about 40 or so, 30, 40 nanometers in diameter. The upper limit is going to be about 1,000. It has to do with anything that retards the Brownian motion and being able to track that movement on a frame-by-frame basis. The particle needs to move a certain distance in between frames to be tracked appropriately. The Zetasizer can go down as low as 0.6 nanometers, just to make sure we're clear about the unit there, 0.6 nanometers up to about 10,000 nanometers. So we published a paper back in 2010 in the Journal of Nanoparticle Research, where we looked at sucrose. Sucrose, is about 0.6 nanometers, and we compared it and verified it with mathematical modeling. Mathematical modeling would give you angstroms. We make that direct conversion to nanometers, and we say, yes, we can indeed look at 0.6 nanometers. On the upper end, it's about 10,000 nanometers. Now, I'll say that there's a couple iterations and a specific cuvette that can actually push that upper limit, and we have the data to show that you can analyze particles up to 15 or 20 microns in diameter. So the range you can see is quite large when compared to the nanosite. So, you're already getting a sense of the respective strengths of both the Nanosite Pro and the Zetasizer. Concentration and size dependence, because you're looking at a number-based distribution with nanosite. If you have a high concentration of large particles and a low concentration of smaller particles, because it's number-based, you can still clearly see those two different populations. But because of the intensity weighting with the Zetasizer, if you have a large concentration of large particles, then you might, you need to adjust your concentration to be able to see smaller particles. Nanosite can work with some pretty dilute samples, and then the Zetasizer can work with some pretty concentrated samples. Samples can look more opaque. With nanosite, the sample needs to look more transparent. Sensitivity to aggregates is low with the nanosite because of the number-based distribution, and there's a higher sensitivity with DLS. And then the additional metrics that you get with the nanosite are concentration, particles per mil for the full analytical range up to 1,000 nanometers. And with the Zetasizer, the other main metrics that you can get is zeta potential. And then there's a couple of the iterations one iteration of the Zetasizer where you could get concentration for a sub-range. But that is my 5 minutes. I'm happy to take questions when we go into the lab. Okay? Thank you. Going once? Okay. So for the nanosite, it's very few consumables because of the top plate design. You have fluidic tube, fluid tip.
This is his
tubing. It'd be syringes, 1 mil syringes. That's how you actually produce a sample. It goes on a pump. Here's on a pump. Blow the sample while you're analyzing it. So very few consumables. Maybe like if you're not careful about cleaning, you just have to replace some of the tubing. With the Zetasizer, it's if you're using aqueous-based samples, then the sizing cuvettes are plastic cuvettes that you would use one and done. And then the Zetasizer cuvettes and some of the other cuvettes are reusable. So very few consumables. Maybe 3 minutes. Maybe a little more with the Zetasizer.
Okay, maybe we can. Okay, next one we still have time for. So the next one is still melted. It's a different type of instrument.
Yep.
Jack.
Yep. Thanks. Yeah, thank you. My name is Jack Sodom with Micromeritics Instrument Corporation, now part of Malvern Analytical. You can see our new logo is a bunch of logos on there. So what I'm going to talk about is surface area and density. Why surface area? I'm going to kind of rush and just get all these on here. But when we're talking about surface area of particles, we mentioned particle size, but surface area tells you the extent of the surface of the material. That's where the reactions are going to occur. So how much surface is there is important information to understand. Typically models for particle size will give you a spherical diameter, but particles are rarely spherical. So knowing how much surface is there in terms of meters squared per gram is an important measure to understand your material. The way we measure it is using gas absorption. These are two common gas absorption instruments that Micromeritics offers, the TriStar and Gemini. We're not going to have one of these here, but I got plenty of videos if you have any questions about them. I'll be talking about them again tomorrow, and we can discuss them during one of the breaks. But the other instruments are for density, which will also give you a porosity value. AccuPick and GeoPick. AccuPick is a gas picnometer. It gives you true density or skeletal density. GeoPick gives you envelope density, or if you're looking at powder, like a bulk density of the powder, like a packing density. Just a little bit on the differences. True density or absolute density, you think of it as the chemical density. Skeletal density would be, it would include the volume of the pores. So if there's any cavities inside the material or internal porosity, that's going to be counted as the total volume because the gas can't get to it. So we're looking at gas displacement and measuring the volume. We know the volume, we know how much mass we put into it, and we calculate the density. For envelope density or the GeoPick, it does envelope density for solid bulk pieces like tablets or pellets, things like that. It'll give you the envelope volume and envelope density. If you have a powder, it'll be like the tab density, which is like a packing density or bulk density. The instrument we have upstairs that I'll show you is the AccuPick. We'll go through a little bit on that, in more detail during the demonstration. But it measures volume by gas displacement. You have a sample chamber of known volume. You have transducers that measure pressure. We have a reference chamber. So we're looking at Boyle's law, P1 V1 equals P2 V2. We know the pressures. We're measuring those pressures. We know one of the volumes from the calibration, and we're looking for the unknown volume. And that's how it determines the volume of the material, known material. And then, like I said, when we know the mass, how much we weigh it out and put into the instrument, we can calculate the density. That's it.
Yeah, it's up here. It's just not up there. There it goes. Good. Okay, so the last Malvern instrument that's upstairs is the Spraytec. My name's Dan Beach. I am a senior scientist as well. The Spraytec does droplet size distribution, which is probably of great interest to a lot of folks working on aerosols, right? So it uses laser diffraction to do that. So on the kind of the near part of the screen, we have a helium neon laser, and then where you kind of see the red laser up there on the screen is where your spray or your aerosol would pass through. So it can pass through vertically, horizontally, or on an angle. The nice thing about the Spraytec is it's kind of an open bench system, right? So those two pods that you see on the rail can slide back and forth. So you can adjust your working distance based on the width of your plume that's being generated. There are two different lenses on this instrument. So the 300 millimeter lens goes from 0.1 micron to 900 micron, and the 750 millimeter lens goes from 2 micron to 2000 micron. So more or less any kind of droplet that you are forming, any size droplet you're forming, we can make the measurement very, very easily. These are real-time measurements. They can take as little as about a half a second to make a measurement, or we can run it for as much as 5, 10, 15 minutes if that's something that you would like to do. Why do we care? I think a lot of people in this room already know why, but in the pharmaceutical industry, it's an FDA required test. It can do a lot about aerosol performance, right? Whether or not you're respirable, if you want to be respirable or not be respirable. And then outside of the pharma space, right? So outside of the nebulizers, MDIs, DPIs, and NEBs, it can also be used for fuel injection, agrochemical sprays, household and domestic sprays, things like cleaners, right? And it's used in spray paint as well, and then food applications such as like the wax coatings that they put on fruit. So pretty much any type of aerosol that you generate, this instrument can measure. It can measure it in real time and give you very valuable feedback. That's the last. Moving along quick.
Into next one. And at the same time, any quick question? Now we will go straight forward with next.
Thank you for getting the presentation up at short notice here. So I'm going to be showing a Nexus upstairs. This is our rotational rheometer. You can measure low viscosity liquids like water all the way up to solid materials with different measuring systems. So the bottom part on the slide there, number 8, is the temperature controller. And this could be modular. You can pull it in and out. And you can measure down to minus 40 degrees C. Or if you put a high temperature oven in there, you can test up to 450. So we can test any liquids or hydrogels or any sprayable materials. At the top, we have the torque head, which is an air bearing. So you could test low viscosity liquids easily, but also it can do strain and shear rate control as it's a digital instrument. And so it's very modular and easy to drop out different geometries or put in different temperature controllers. And I didn't bring this because it's rather large, but we do also have capillary rheometers, and these are of interest to sprays because you can generate the high shear rates that you get with a spray. So you can generate over 1 million reciprocal seconds with a capillary if you put the sample through a small die. And just looks like a big box, so I thought I'd bring a cut-out picture of it. So basically you have a tube here, you've got a pressure transducer on the side at the bottom, and the die right at the bottom of the tube. You can switch out the die to make any diameter. So if you want to extrude a polymer melt, you can with a wide die. If you want to put a thin die on, then you can spray things through a 100 micron nozzle. And you could get to, I think, about 100 million reciprocal seconds. And we've got 2 barrels, as you see, 2 holes through this. That's so you can do the entrance effect correction. So you get the entrance and the whole shear, and then just the entrance effect if you choose a short die. And then you could get the true shear viscosity. And so together, you can get from ultra low shear rates up to ultra high shear rates and see sedimentation, stability, sprayability, freeze thaw, rebuild time, all kinds of things like that. So I'll be talking about that tomorrow in my talk. Thanks.
So specialized developing instruments to do characterization of web mount for the cell PSI. We also have a small particle sensor. So we saw this morning that the system our there's a small box. She has 90% of the instruments that the company sells. So when we come up to the lab, we will be able to see all this. So basically, it's we do from physical characterization, counting, and testing. We also do history, do headline researcher, the research company. So we also toxicology. All these instruments, except for the all the rest of it.
Any question for ADI? Okay, if not, the next one, Quant AQ.
Let me share the screen. Oops. Yeah, we're good.
easiest to. Nope.
No, the mouse. Only the mouse.
Great. Okay.
We want to go to PowerPoint. You can also.
No, that's fine. Yeah, that'll work. Make it work.
Just zoom out.
Awesome. All right, well, I'll do it with the mouse. Not quite line up, but all right. I'm David. I'm the CEO of QuantIQ. We are a startup spun out at MIT about 8 years ago now. We are a group of mostly scientists, you can see here, with a few other engineers and sales folks thrown in. And we primarily, our goal is to make it as easy as possible to make as many air quality measurements as you can anywhere you want or need. Our specialty is building internet connected devices, specifically for outdoor ambient use cases. Oh, one more thing. We're hiring. So we've got four jobs posted. If anybody's looking for work, specifically in the air quality and aerosol space, come talk to me or find us online and we can get in touch. So just a very macro level view of what we do. We currently have 3 primary air quality sensor products: Modular, Modular PM, and Modular UFP. The Modular and Modular PM are our oldest products. We've been selling them for 6 to 8 years. Both of them share the same core particle sensing technology, which we developed, which is light scattering based, very similar to what the team was talking about earlier. The difference is we combine single particle scattering with nephelometry, overlay those spectra, do some physics magic, and that allows us to measure both fine and coarse aerosol simultaneously, which is really handy. The Modular also measures for gas phase pollutants, CO, NO, NO2, and ozone. Everything is designed to be low power, again, internet connected via both satellite Wi-Fi, very easy to set up and use in outdoor environments. And about 6 months ago, we started selling the Modular UFP, which is an ultrafine particle counter. So it's a water-based CPC developed by ADI. And we are very excited about that one. So far, we've got about 50 or 60 of them deployed in the United States, and looking to grow that quite a bit this year. Our other is on the software and data science side. So for both ourselves and our products, as well as working with other companies in the space, especially other smaller manufacturers of kind of niche aerosol products, we help them take their instruments, connect them to the internet, bring them online onto our platform so that it's easier for people to use them and deploy them in remote environments. And that's pretty much all I've got for you. We're based in Somerville, Massachusetts, right in between MIT and Harvard. If you're in town visiting Aerodyne or anyone else, we say hi. Yeah.
Okay, so moving from startup, we are going to do PSI.
Yeah, or use this left click one. Okay, or the scroll.
How do I go back out? Just, there we go. Good afternoon, everyone. Todd Gack, Southeast Particle Sales. So at TSI, just want to give you a general 10,000-foot view of the company. This is a picture of the front of corporate headquarters in Shoreview, Minnesota. Industry leader in the design and production of precision measurement instruments. It's founded in 1961 by University of Minnesota graduates. Company has about 1,200 employees worldwide. The headquarters, as I said, is in Shoreview, Minnesota. And from this world map, you can see that we're stationed strategically throughout Asia, Europe, and the US. Oops, sorry. So as far as particle instruments go, our main areas are filter testers, aerosol generators, particle counters and sizers, and sampling accessories. Applications are indoor, outdoor air quality monitoring, engine emission, aerosol research, which that picture is kind of near and dear for me. It's for those of you that have traveled to top of Europe, you might recognize that. That's up on top of Jungfrau. It's a research station that one of our colleagues from Japan actually had the opportunity to work at for like 6 months. Ambient air quality, filter testing, and inhalation drug development as well. As far as our automatic filter testers go, 8130A is a benchmark flat media and commercial respirator tester. Behind it there, you can see with the head form, that's our 8119A, which is a respirator leak tester. The 8150 is a production line tester used for quality assurance testing of materials such as P100 and similar respirator filters and cartridges directly from the product production line, as you can see in the two bottom photos. And the 3160 is our fractional tester used to challenge filter and filter media with submicron aerosols. All of these instruments are on the more expensive side. Did I skip one? Okay, this didn't come out color coordinated, but that's okay. So generally speaking, this is about the portfolio of the instruments that I handle. So we sell aerosol generators that generate aerosols from 2 nanometers and up, aerosol counters from 1 nanometer to 3 microns, aerosol sizers 1 nanometer to 20 microns, and then a plethora of accessories from diluters, neutralizers, dryers, and tubing. Oh, there are my colors. As far as aerosol generators go, dry powder, we've got 2 versions, the 3410U, the 3410L. These are continuous stable dosing with high accuracy depending on your mass concentrations, which are expressed here. The fluidized bed generator is 3400A. That prepares any powder in a gas form. These are constant output, good for inhalation studies, tox studies, that sort of thing, filter testing as well. Also for liquids and suspensions, depending if you're looking for polydispersed or monodispersed. Again, I'm not going to get into all the numbers here, but you can see that there's several options under the polydispersed generators as well as the monodispersed. Particle counters, we've got quite a few of them. The 3002 is our latest portable water CPC, which we'll have upstairs for people to take a look at. Then we have your traditional, in the green box, would be your the butanol water working fluid. I'm sorry, butanol working fluid. And then on the far right are our water CPCs. Particle sizers was quite a bit, a lot of information here. This can be found on our site. I'm not going to go through it all, but probably many of you are familiar with our APS, probably our OPS, our SMPS series as well, and our NanoScan SMPS portable. We have the Fast Mobility Particle Sizer upstairs, which I don't know if you can see it with that talking symbol up there, but the 3091 will be demoed today. For those of you interested in cascade impactors, we got a plethora of those from our sister company, MSA. We have both the non-rotating and rotating, depending on what your cutoff size is. We might have something that can help you out. So what's new? The OmniTrack, it's been around for a while now. It's just started to enter into my value stream. It's a user-intuitive solution that can measure indoor air quality parameters used for air purifier verification, IAQ studies in multiple environments, from schools to hospitals to you name it, and industrial hygiene. It's a wireless connection between the OmniTrack and the modules. There's up to 10 modules.
So all of these 10 modules could be placed in various locations independently and transmit data back to the smart station. The data can then be downloaded directly from the device onto your PC, or you can upload right to TSI Link, which is convenient for report writing because it's all done in Word. And then lastly is our portable water CPC, and I'll just list some of the features for all of you so that when you get upstairs, you take a peek. It's a 2-channel system for simultaneous measurements from different locations. It's battery operated. It's got about a 4-hour battery life. Lightweight, portable, so it's great for field work. You can jostle it around because it works off of wicks. Wick life is about, it depends on your relative humidity, but that can be quite a long duration of time. It's got potential drone use applications, hot swappable battery, easy data management with Bluetooth and USB-C. It's got onboard data storage with 3 operation modes. Comes with software, PC software for data collection, access and export. Suitable for concentration levels up to 2,000 particles per cubic centimeter. It's cost effective, environmentally friendly, and uses distilled water. Weighs 2.2 pounds, so again, drone applications potentially. D50 is less than a 10 nanometer size particle, and the wick life about 8 hours or greater, depending on relative humidity. Along with me is Justin Kozak, application engineer. He's the brains behind the operation, so he's your man. Thank you.
Okay, we'll get back to stop.
Left click, and then the scroll. Cool. Sure.
All right. Good afternoon, everybody. I'm Collins. I'm the founder and president of OpenAeros. OpenAeros is an open source aerosol hardware company. And we're going to talk, we have a demo upstairs for the Open CPC. Our claim to fame is a low cost or lower cost, depending on who audience you're talking to. I think in this world, we're low cost relative to the stuff I saw before. And we make a low cost condensation particle counter. We call it a CPC. Oops, I hit the wrong button. So then I did the wrong thing. Look at me. All right, technology. All right, there we go. Okay, so we're going to talk a lot about it up there. You'll get probably more interested in who is OpenAeros. So OpenAeros is founded on the fundamental belief that we think that clean air is a human right. And the challenges in the world right now are really being dictated by the things we breathe, whether it's the pandemic, it's wildfire smoke, it's microplastic, it's climate change. Right? We just heard of talk about how trying to model particle formation is changing the way that we think about climate change. And so what we want to do is help usher in much faster transformation. I think that the timescales we need to do and solve this need to happen. We think that open source hardware and software are one way to do that. And that's because we can improve, you can increase the availability and access of instruments. It can make them less expensive. You can get a pathway to global adoption. You can scale it at a much faster pace than traditional business models. And you can be transparent. I don't know how many times you've ever worked with like Purple Air and the black box algorithm of the PMS 5003. It's a little frustrating. So the Open CPC was about filling a gap that we saw in that space of a fully open source CPC that reduced cost. And I think what's interesting is, we see this a lot. I thought this paper was really interesting in the bottom right that just came out last October. They took subjects, did blood draws, then stuck them outside, standing next to a roadway in London, and then drew their blood again. And then put it in a SEM and compared those pre and post. And what they found, those are red blood cells. And those little black things are ultrafine particles from the roadway emission that was in their blood after exposure. And I think that's weird. We all work with things that are invisible. We all develop instruments because we can't actually touch or see the thing that we're working on. But I think it's really eye-opening to be like, yeah, the stuff we're breathing in, it's in us. It's causing problems. It has health impacts. I'm not going to talk a ton. Oh, I should pay attention. I'll talk a little about the performance and specs of the CPC. It's a 10 nanometer to 1 micron total number count from 0.1 to 100,000 particles per cc. So if you compare that to traditional condensation particle counters on the marketplace, we're very competitive in terms of performance. We are a little weird. We use isopropyl alcohol, which is it was an intentional move. Runs on 120 hours with a fill. We'll talk a lot about that upstairs, but okay, what does that mean to you all? It's lightweight and easily transportable.
It's quiet. That's kind of one of the did that so you could do indoor monitoring. So it's quiet. We don't have butanol because it's odorous. So can we start to think about indoor monitoring of ultrafines? You'll see upstairs, it's a simple and robust design. There are no fill pumps. There is no fill bottle. There's all kinds of a lot of complexity we took out of CPCs. And we designed it for any level researcher, whether you're an undergraduate who has never worked with aerosol science instrumentation, or you are designing your own instrumentation and you want to use our high-speed Python library. Like, we want to cater to all those people. But the biggest thing is that it's inexpensive. And we're one of the few companies that will tell you how much it costs. You don't have to call or talk to a salesperson. It's also available on our website. Mouse button. Okay, so also I wanted to, so why are we doing this? And why do I think open source is really cool? I know people are developing instruments here today or thinking about doing it. I want to pitch you on why open source is super cool and a different way to think about problems. It doesn't work for everything, but if you're thinking about it, I can obviously give you some details. So why do I think open source is super cool? One, think of it as, think of it as a really detailed user manual. You get a user manual today, you look through, you're like, okay, but then you're like, well, how do they do that calculation? When you open source it, you can go to our code and figure out exactly how we compute stuff, how we measure stuff. That's our amplifier circuit for the photodiode where it collects scattered light. There's the schematic. There's the chip for it. You can take this design and integrate it into something entirely different. So we can grow a community that's building instruments that can see what we did and help you design your next instrument. I just ask that you do that same for other people. Take your design, open source it, help the next person. And if we all work together, we can really accelerate sensor development. So there's a photodiode circuit. Here's the schematic. So if you need to know where U4 is, let's see, U4 is our input. Actually, I lied to you. It's on the back side of that board. So that was a great image to use, but U4 is on the back side. These are our negative. Okay, so you can integrate these into other instruments. That's really cool. It's easy to do it if it's open source. Make it very transparent how you do it. Biggest thing though, and that's why I love open source, is let's grow. Let's create a community that helps us solve one of society's biggest problems right now. And if we can share, we can all share, we can make better instruments, we can do it faster, we can do it cheaper, and we can save people's lives. So we're going to talk a lot about more OpenCPC in the demo, and I kept it to a few minutes so that we can all get upstairs and play with some fun stuff. Now, our second one.
Button or scroll. Okay. Okay. Yeah. Thank you very much. Hello, everybody. My name is Volker. I'm at Pallas responsible for global product management, head of product management, and also for the sales. And I want to introduce to Pallas a little bit because I think the brand itself is not so much known in US. Okay. Okay, what are we doing with what kind of instruments do we have? So we are developing and producing instruments in Germany. Our main company, our main production site is in Germany. We have a very broad portfolio from aerosol generators to aerosol spectrometers and also to nano instrumentation, but also we have an industrial side where we produce also filter test rigs, filter instrumentation, and we have also services like cloud solutions, etc. Founded 83, so around about 40 years ago. Bratin Biswas this morning mentioned the future for in optical systems with polychromatic light. You can see how the future is working because we are working since 40 years with polychromatic light. We are not using laser light. We are using, at the beginning, it was xenon light, but this is the portfolio, and I can show you then later on the advantages of these solutions. We are located in Germany, but we have also a subsidiary in China, in Shanghai. Aerosol spectrometry with polychromatic light. I just want to highlight a few instrumentations. We have certified instrumentation for compliance measurements on one hand for governmental applications. We have indicative systems, but we have also research instrumentation, where handheld instrumentation and also for room observation, for example. We have with our Bromo systems, systems which are very robust. We have a big variety of geometries of the measurement cells, dependent on the concentration levels. but also on the flow rates. You can also choose from different flow rates here. And we have also typical or special applications like cloud droplet analyzer, respirometer, or mask Q check. These are instrumentation where spectrometry was combined to develop a solution. I mentioned also nano-instrumentation. We have also here a broad portfolio. CPC, for example, you can use our CPCs. Basically, it's often or mostly used with butanol, with N-butanol, but you can use also diethylene glycol and also water with the CPCs. We can build up this to the SMPS systems. We have all these components, and we have also an electrometer in the portfolio. Here you see different applications, what we cover with our instrumentation. It's very broad, and it is more or less touching different disciplines from medical to atmospheric and climate change research. And now industrial applications. You see also here we have a broad variety of aerosol generators. I think it's 15 or 16 different types of aerosol generators, from solid to liquid, so in solvents. Aerosol spectrometers, but we have also a big variety of test rigs. This goes up to test benches with 5 meters in length and 4 meters in height for industrial applications. So we are also in the automotive industry, working on the one hand for cabin indoor air quality, but also for brake emission testing. And the latest topic which started and which is going to be more and more interesting in Europe, but also in the US, there is a UN working group working for it, the tire operation. Also here we made special solutions for the universities. Okay, last but not least, we have a data platform. We call it My Atmosphere, where all the instrumentation we have, you can connect with the data platform, and you can do the data analysis, data storage, remote also with the data platform. And that's the last slide from my side. You have different possibilities, of course, of analyzing graphical display in the data platform, and more upstairs later. Thank you.